Thank you and good morning to everyone. Welcome to day 2 of our workshop. We have a jam-packed second day filled with topics such as sensors systems, informatics, data science, computational neuroscience, and behavioral neuroscience and related experiments. So to get us started again, I'd like to welcome Dr. Holly Lisenby, who's the Division Director of Translational Research at the NIMH.
So thank you, Yvonne. It's so exciting to be launching day 2. Day 1 was really fantastic. I'd like to thank all of the speakers and attendees for your great Q&A, and we're looking forward to another exciting day. I want to start by thanking the members of the Workshop Planning Committee for BBQS sensors, and they really span multiple NIH institutes, offices, and NSF, starting with, of course, Dr. Yvonne Bennett, Dana Schlosser, Lizzie Ankotovich, Svetlana Tasiklushi, Yun Liu, Brooks Gross, Carrie Ashmont, Tristan McClure-Begley, Sandeep Kishore, Aaron King, Holly Moore, Elizabeth Powell, and Aaron Burke-Quinlan. This really could not have happened without you, so thank you so much. Now it's my pleasure to introduce the moderator for this morning's opening session, Dr. Carrie Ashmont. Dr. Ashmont is the translational team lead at the National Institute of Biomedical Imaging and Bioengineering, or NIBIB, as it's affectionately called, where she manages the NIBIB Small Businesses Program, including the Concept to Clinic Commercializing Innovation, or C3I program. She also supports the Institute's RADx Tech program and co-leads the dissemination programs for the NIH Brain Initiative, highly relevant for our topic today. I got to know Carrie when she was at NINDS, where she oversaw the Translational Device Cooperative Agreements and ran the NIH Blueprint for Neuroscience Research Education Program on Translational Devices, or the R25 program. Dr. Ashmont has degrees in mechanical engineering and biology and biomedical engineering, so her expertise is perfect for today's session. Welcome, Dr. Ashmont.
Thank you very much, Holly, for that wonderful introduction. And good morning, everyone. It is my pleasure to introduce our speakers for this portion of session 3 today. We have Shangji Li from Texas Tech University, who will discuss portable radar systems for non-contact continuous measurement of naturalistic behaviors and physiological signals. And we also have Roozbeh Jafari from Texas A&M University, who will discuss digital medicine for cardiovascular health. With that, I'll pass it over.
Thank you so much, Carrie, for the nice introduction. Good morning, everyone. So my name is Changzhi. You can call me Chen-Zi, or you can call me Chaz. Make it easier. All right, there we go. So to begin with my presentation, I'll play a video taken on my daughter, Chloe, when she was less than 1 year old. And this year, she's turning into 10. So you can calculate approximately when this research was done. So one night, I brought a device designed by my students back home. And after Chloe, also my wife, went to sleep, I secretly hung the device on her crib and placed the laptop over there. So as you can see on the screen, the device was hanging on the crib, looking at Chloe, about maybe 40 centimeters away. And on the other side, on the laptop, you can see a real-time signal on top, time domain, and on the bottom is the FFT result. No other signal processing. Basically, using radio frequency signal, it's possible to pick up the respiration and heartbeat of a person without anything attached to the body. And what is surprising is this is actually not new. So back in 1975, Dr. James Lin invented this respiration detection system using a very bulky microwave system. Okay? And what really made it amazing was in 2002, the group of engineers at Bell Lab, actually including Dr. Zhenshan Lin, my advisor, integrated the system into CMOS chip. And I started my PhD career in 2005 with Zhenshan in Florida. And today, Zhenshan has already retired and joined the NSF as a permanent program manager. After this, really in the past 10 years, we have seen tremendous advancement in this type of technology, as I will show you later today, right? So the mechanism here is actually quite straightforward. Basically, we have a radio frequency sensor, we call it radar, and the radar sends out a radio frequency signal towards the human body. And once the signal is bounced back inside the receiver of the radar, we compare a local copy of the transmitted signal with the received signal. And based on engineering processing, basically we can figure out the signal phase change due to the propagation along the way. Okay? And because of that, the small motion of respiration and heartbeat will show up in the detected signal. Okay? I'll skip the details, but from engineering point of view, we have lambda representing wavelength in the detected signal. And if you look at the equation, obviously, if you reduce lambda, the wavelength, you can make the phase modulation bigger. And because of that, you can increase the detection sensitivity. Okay? So increasing frequency, pushing this into millimeter wave range is a way to make this really, really sensitive. And this is the effort done by a lot of RF engineers in the past 10 years. Another thing I want to mention out is the transmit signal power here is more than 1,000 times lower than the peak power of a cell phone. Moreover, we are detecting a really slow movement, 1 hertz or 0.1 hertz. So we can heavily duty cycle the transceiver to make sure the average radiated power is really, really low and makes this really safe for human and animals. Okay, and we call that vital Doppler. You use Doppler effect to detect vital signs. Another application is called MicroDoppler, and now we are talking about bigger movement. For example, if I swipe my hand, there is movement, there is speed, and that's going to induce Doppler information. So shown here are 2 examples. In the first example, we had the radar in front of this person. This person first sit down and then raise the hand, put down hand twice. So on the right-hand side, we are plotting the Doppler frequency component as a function of time. As you can imagine, if this person sits down, then the distance from the radar is going to increase, and that's going to induce a negative Doppler. But in the meantime, interesting thing is when we sit down, our head is going to lean forward a little bit. Therefore, there is a weak positive Doppler. And then over there, you can see the signature corresponding to hand movement. On the bottom side is a very similar demonstration. So we had a person who walked away from radar, generated a negative Doppler, and then this person pushed both hand twice. You can see those information over there. And after that, this person walked back towards the radar. Okay? And leveraging this type of micro-Doppler effect, the industry is also doing a lot. For example, to move to the next slide. It looks like a computer is frozen. Oh, it says a restart program from the computer screen. So I'll restart the program. I apologize for that. And I believe the operator is helping me to restart the program. Right, great, excellent. Thank you. And I apologize for the inconvenience. All right. And if we move on to the next page, you will see Google has a team called Google Sorry. They leverage this to monitor hand gesture and use that to interface with smart devices. And the goal is that you don't have to touch the screen. You don't have to mess with small buttons. You can control the device remotely. And 4 years ago, Google had their Pixel 4 phone put on the market. And in this Pixel 4 phone, you actually have this radar sensor, the green color shown over there. And for this radar sensor, it can pick up hand gesture. You can remotely activate the phone. You can play music, volume up, volume down, things like that. And the engineer in Google who integrated the radar into the phone was actually a PhD student who graduated from Texas Tech, right? And unfortunately, nowadays, Google is pushing for lower cost. They removed the radar sensor from the phone, but they are working on integrating this radar sensor on other products, including Nest for smart home applications. And all of this is really dependent on the aggressive progress in the past years in the semiconductor industry. So for example, back in 2017, during International Microwave Symposium, TI demonstrated their 77 gigahertz radar system. And nowadays, this is quite popular for researchers doing radar IoT smart application research. And Infinium is the company that provided radar to Google. So they demonstrated their 60 gigahertz radar chip. So their chip was over there, connected with the tablet. And in the conference, their engineer can train the attendees in 1 or 2 minutes. Then you can master a lot of hand gesture command to interface with the tablets. And analog devices also have their 2477 gigahertz systems. Okay? In 2021, Infinium actually put the system in a very small module. This is 1/3 as the size of a business card. And with that, you can plug this into laptop. And a lot of researchers not familiar with hardware can do research using radar sensors. Okay? And I mentioned that if we increase the carrier frequency, we get a higher sensitivity. So here, this student, Daniel, first demonstrated using a 125 gigahertz radar sensor, he can achieve a sensitivity as high as 95 nanometers. And using that, he pointed the radar towards his throat, and he said one sentence, "I am a boy." On the right-hand side shows the spectrogram detected by radar using 2 different methods. You can clearly see, "I am a boy." And on the bottom side is the detection results coming from the microphone of the smartphone. You can still see "I am a boy," but you see a background noise, a flat line over there. And this is due to the ventilation fan in the room. So basically using radar, you can achieve highly directional detection of small motion related to human bodies. Another big application of radar is you can easily detect the distance. So in this demonstration, we had a radar in the center of the room. We scanned the room for 360 degrees. And after that, you can see a bare layout of the room. This is not awesome because the resolution is not high enough. But what is really wonderful is, as I mentioned, we have vital Doppler. And using vital Doppler, we can easily differentiate between human subjects and other stationary objects. So with very little computation, we can achieve human-aware localization. Okay? And the next page shows a demonstration. Oh, seems it's stuck again. All right, yeah. Oh, there we go. Okay, so this suppose should be a video, and I hope it's gonna play. In this video, basically we have 2 people walking back and forth. And in this very narrow corridor with radar, MicroDoppler, and range Doppler, what you can see is here, if you focus on the lower left, you can see the 2 people walking back and forth. And all the clutters are naturally compressed into the horizontal line, because in this video, we plot the Doppler as the vertical axis and the range as the x-axis. So all the non-moving clutters are on this horizontal line with 0 Doppler. We can easily extract human information. And this experiment was done with a small radar device at 5.8 gigahertz. As you imagine, if we push the frequency higher, we can have higher resolution in showing where the people are without using cameras. Okay? And leverage that, we can think about healthcare applications. So one demonstration here is consider the scenario of a person who is falling. Okay? If the person is falling towards radar, the distance or the so-called range is going to reduce. The Doppler will increase because the speed increases. And the signal will become weaker as the person lies down. So basically, we leverage RCS, radar cross-section, range, and Doppler to achieve the detection. If you plot the result on Doppler range video like that, you will see the dot moving this way with reducing range, increasing speed, and the weaker signal. If the person falls away from the radar, you will see the dot moving in opposite direction. And in the bottom side shows another case, this person made a small move, not falling. So definitely the difference is very significant. And next page shows experimental demonstration. On the top side shows 4 frames of this type of radio frequency video. You can see the signature started from here, and eventually it moved, the signal started from the upper left. Eventually, it moved towards that direction and then disappeared. That's the first row. And in the middle row, the signature actually moved in the opposite direction. The bottom row shows experimental results of a small jump. Okay, and in order to make this really applicable, you have to think about a continuous monitoring situation. And in that case, we can extract the location of that energetic point, get the range Doppler, and plot the range Doppler in the range Doppler time frame, which corresponds to the lower left 3D cube. So we have Doppler information, we have range information, and we have time. You will see that dot moving around. And applying machine learning, it is possible to characterize and classify different activities in a continuous environment. Okay? And now we come to my favorite page, because this research was done by a high school student girl, Rachel from Irvine, California. She stayed in my lab in the summer for 7 weeks. And what she did is she used a radar to look at a person in a car when the person is driving. When we drive, sometimes we pick up phones, we look around, we dance with music. So you will see different activities. But there is one behavior that's really dangerous, the upper left. If the person falls sleepy, then the head will drop. So Rachel found out, definitely, if you look at the Doppler as a function of time, different behavior is going to give you a different signature. And using that, you can differentiate those things. So she published a paper on IEEE Radio Wireless Week. And after that, a PhD student took over the work, applied the data to machine learning program, and demonstrated you can automate this type of detection. Okay? So Rachel actually did this in 2018. She joined MIT in 2019, and this year she finished her degree in ECE and biomedical engineering, like 2 degrees. And she was selected as an MIT Oxford Marshall Scholar to continue with her training in biomedical application and medicine in London. Okay? She also interned with NIH in one of the summers. So next page is another work done by a high school student, Hannah from Philadelphia. So last summer, she stayed in my lab for 7 weeks. And she likes to play violin. So I said that, why don't you bring this radar into your dorm? So the setup is shown over there. She had a small Infinium radar looking at her while she was playing violin. And with the radar, she was able to record different data. And she was awesome, applying this into machine learning. And 2 days ago, her paper was officially published on IEEE Sensors Journal. In the May issue. She was also admitted into MIT last November, got an early admission. Okay, so what I want to really point out is over the past 10 years, there has been aggressive progress on system engineering, integration, and semiconductor. Because of that, you will see this type of research is definitely doable for people not familiar with semiconductor engineering or radar systems. Okay? And the last page on research, I actually stole one page from JC. So microwave can not only be used for remote detection, you can also use that for wearable detection. And here just showcase a simple example JC's group is doing. Like they are using microwave sensor to detect dehydration. And you've got to talk to him about how interesting it was for the researcher to be dehydrated in order to carry out this research. Okay? And the future outlooks, the advantage of microwave system is it's non-contact, continuous. There's no image, so it protects privacy. It's non-line of sight. Okay, and we're also looking at other applications. This is a recent result. We're going to present in the International Microwave Symposium. So we have 2 radar sensors on the glass frame to monitor eye movement. Hopefully, this can be connected with people with neurodegenerative disorders. Okay, and finally, thank you so much for your attention. I really appreciate it. And with that, I guess today Carrie is going to introduce our next speaker. From the other side of Texas. Okay, great. So next speaker is going to be Dr. Roosevelt Jafari from Texas A&M University.
It's a pleasure to be here today. Thank you so much for Dr. Bennett, Dr. Sculptor, and Ms. Robinson for the invitation and organizing this wonderful. Oh, sure, absolutely. Can you guys hear me now? Is it better? Okay. I just wanted to share my gratitude with Dr. Bennett, Dr. Scorser, and then Ms. Robinson for the event. It's wonderful to be here. Let's talk a little bit about, I'm going to talk, my talk is broader today. I'll talk a little bit about digital health and wearables. And I'm going to start with the motivation for wearables. Watches are one of the first wearables that we started carrying with ourselves. The reason that we have a watch is not because we want to carry a piece of jewelry or electronics, it's because we want to receive the time. When we look at the history of watches, we used to have these pocket watches, and they were small enough for over a century. People actually could strap them on the wrist. But at the time, the society was unfortunately mostly male-dominated, and they felt that it would be a piece of jewelry to put a watch under. And it wasn't until World War I when the soldiers realized that, hey, I'm on a horse. I need to synchronize myself with the rest of my team. It's much easier to look at the time here as opposed to getting it out of my pocket. And then right after that, we went into Industrial Revolution. We used the notion of time to synchronize ourselves. Time is actionable. I look at the time, I get up, go pick up my daughter, or get on the next meeting. And then the interesting part is actually it did become a piece of jewelry. A watch, $15,000 is not about the time. So the work that we do in this field, collectively, I have the opportunity to interact with the digital health community. I was the inaugural chair of the digital health study section. Is always driven by actionable information. And the information needs to be accurate, reliable, to enable precision health. I want to just bring up the fact that I'm using the word precision health and not precision medicine. Equity, access, and scale are really important. We have a little bit of chicken and egg problem here too. A lot of technology development is based on AI. The data for AI comes from all of us. We have to convince individuals to capture that data. But at the end of the day, at the onset, you don't have the value proposition to wear these sensors. So these are some of the important directions where we rely on the investment and the vision of NIH, ARPA-H, DARPA, and many other institutes that would help us to take it over that barrier. One thing I'd like to sort of share with you all is that the purpose is never to replace the medical diagnostic process. Physicians and nurses, highly intelligent, highly trained individuals are not going to be replaced, not the sophisticated equipment that we have in a hospital. The purpose is to use this Oura ring that I'm wearing here to detect the pre-symptoms of COVID-19, the onset of disorder, so you can take a quicker action. Or when you go through the intervention, assess how well it's working. So again, this is a collective view of the discipline, but at the core of digital health, we have the human state. We're trying to read from human, determine the physiological, behavioral, or contextual state. The work that we do is always driven by actionable information. In my career, I have built a bunch of hammers looking for nails. It didn't work out that well. So building sensors, I'll talk about some of those today. A good portion of these studies are actually sponsored by NIH. Working with electronic tattoos, building sensors for blood pressure using commercially available devices, understanding what it is that we sense. Believe it or not, there is just still a lot of information that needs to be captured. Signal processing is typically extracting signal and removing the noise, and analytics is typically personalization. How do you compare apples to apples over time? And how do you build algorithms that would be customized for each of us? So let's talk a little bit about the blood pressure. When we started this project back in 2013, I didn't know why the blood pressure was so important. So I'm going to just go over this very briefly. At the core of our cardiovascular system, we have the heart. When the heart is beating, we have a heart rate, and then we have a stroke volume. Combination of those two is going to give us the cardiac output. That's how much blood is leaving the heart per minute. Now, our cardiovascular system is extremely amazing. When the blood goes into the arteries have what is so-called peripheral resistance or peripheral compliance. They are not like a solid pipe. They expand a little bit. The leading cause for elevated blood pressure, hypertension, is not actually the heart typically. It's arteries. They become stiffer. And over time, the body is a feedback system. The heart also becomes a stronger muscle, and we end up with a sustained hypertension. So blood pressure is a time series signal. You get a signal that would look like this if you look at the left ventricle. The blood pressure changes for every cardiac cycle. If you're lucky, We capture this once or twice, and we only capture the systolic and diastolic. There is a significant need to look at the entire wave. It's important because BP, blood pressure, is the most important biomarker for heart disease, and heart disease is the leading cause of death with a significant financial toll. The work that we are doing also is going in the direction of measuring advanced hemodynamic parameters, including arterial stiffness. We talked about it last night. You might have heard stress kills. We don't know how, but it has to do with arterial stiffness. This is also another picture of a favorite of mine that I received from Dr. Arshad Kuyumi at Emory School of Medicine. This is all of us. We go through this process. When we are in 20s, that's where we are on the left. And then as we get older, we go through this. We want to be able to measure that and characterize it. So blood pressure was invented in Austria in 1881. The difference between the original blood pressure device and what we have right now is only the new one doesn't have mercury because it's toxic, but the technology is the same. You place a cuff on the wrist, you inflate it. At some point, you do not hear the pressure, you do not hear the tone. You start deflating it. You hit a point where you hear the first tone, that's your systolic high blood pressure. At some point, you do not hear the tone anymore. That's your diastolic. And then when you hear the maximum tone, that's your mean arterial pressure. This technology doesn't work as well because you get very infrequent measurements. We have what is so-called mask hypertension. You take the blood pressure is not high. I go see a doctor, my blood pressure goes up because I see a white coat syndrome. So this is not very accurate. And then, there are studies that show, this is Dublin study, looked at ABPM, ambulatory blood pressure monitor at nighttime. And then they noticed that nighttime blood pressure measurements is actually the most predictor of cardiac disease and the outcomes. These are, ABPM is a device that you put it on. It gets activated every 30 minutes. It's actually fairly inconvenient. I have used it myself to understand the limitations. Sometimes it wakes you up and your blood pressure goes up because you're upset. So our take on this has been to use the bioimpedance and measure the blood volume changes. We use 4-point sensing here. I don't need to go into the details of it, but we extract a number of parameters, including the pulse transit time on the radial artery. And then you get a signal on the bioimpedance that would look like this. It's a time series signal with a diastolic phase, systolic, inflection point, and so on. And then we want to take this signal and then convert it back to the blood pressure. Many of us have these PPG-based devices. They measure the blood, the pulse arrival time. The limitation of the PPG and the optics is that the light cannot go deep into the tissue. We get about 4 or 5 millimeter of penetration if you're lucky. If you look at the fluctuations of the blood pressure, this is the blood pressure in left ventricle, in arteries, but when you get to the capillaries, which are at the surface of the skin, you no longer have the blood pressure. You only have the pulse rate. And it's not okay to try to capture the capillary blood pressure from capillaries. On the other hand, the bioimpedance can go as deep as we want that. And there are two other important characteristics for bioimpedance. One is it's not sensitive to the skin tone. When you go to darker skin tones, the skin pigments would absorb the light and the signal-to-noise ratio drop. That's sort of an equity at the onset of sensor development. Also, if you look at somebody who has a higher BMI, the thicker layer of fat is going to block the lights. And those are some of the challenges that bioimpedance does not. So our take on this is we want to do sort of an imaging. Think about this as a camera. We have an array of these sensors. We do imaging. We try to figure out where we need to focus, and then we capture readings from different sites. The program looks at building sensors. It also looks at the data quality and augmentation, garbage in, garbage out in any AI algorithms. That's a really critical piece. I'll talk a little bit about the digital twin today. And the digital twin applies both to the development of electronics. How do I build the sensors? Where do I place them? What should be the size? As well as the underlying physiology. And then the machine learning algorithms, the localization techniques. How do I do source reconstruction? And then the blood pressure estimation. We build electronics quite a bit. I prefer not to do it, but we have to do it because oftentimes we have to really push the performance of our electronics. Our experiments are fairly sophisticated. In the background, we have a phenopress device that measures the blood pressure continuously. a $50,000 machine. We introduce a number of maneuvers called pressure, exercise, and so on, and we capture measurements from our technology as well as the gold. I'm not trying to discount this field, but I have this example from vision/robotics community. You're trying to build an algorithm that would detect substance. So we have to have 10,000 instances of stop sign captured at different angles, different light illumination, different type of cameras. It's a hard problem, but it's not rocket science. It's more of a heavy lifting. What's the equivalent of this when we think about cardiovascular health? How do I create 10,000 instances of heart failure? I would be lucky if I have 3. And I can't even have 3. I have to start with animal models, because if you know the person is going to have heart failure, you have to take an action. So the data that we have in this discipline is very hard to acquire, highly imbalanced. We have a lot of healthy data points, but the disease state is often more challenging to capture. Everybody is different. So you have a lot of confounders. And then in many cases, you don't even have the disease state. I don't have atrial fibrillation. So how do you build an algorithm to detect atrial fibrillation? So digital twin, who knows about digital twin? Everyone? Okay, great. So this term was coined by NASA in 2010, but they have been practicing it since the 60s. So NASA runs a lot of experiments that is highly mission critical, and you get only one shot. You're sending man or woman to the Mars. The rocket cannot fail, and it takes 2 years to go through that process. The rocket also goes through the aging. So you need to make sure that the rocket is being tested under different conditions. So the idea of digital twin is to create a computational model that remains persistently coupled with the physical system, and then you can put it under different tests. Let's look around. What's the most important motor that you see in this room? Our hearts, our cardiovascular system. So we need to have digital twin for that as well. So I'm going to skip through this. Really, the excitement is all these novel sensors and the AI coupled with the models. The models have been around for a long time, and these models are very comprehensive. But the only way this becomes actionable is when they are personalized. So we need to be able to do this, and that goes in the direction of digital. So in the interest of time, I'm going to skip through this. I have this example. Think about this spring. You would like to know where the mass is. If you happen to have this equation, mass times acceleration, the damping factor as well as the constant coefficient, you can write it and figure out where that spring is. But let's say I don't have this, and I'm going to use a neural net to try to train it. I have data points up until today where I'm standing here in front of you. I trained the neural net based on the classic function, minimize the error. The neural net has no idea this is a spring. But once I take this model and I apply this into my penalty function, now the neural net understands that we're thinking about this thing. That's the kind of mentality that we have when we think about these physics-informed neural nets. So we have been working in this area quite a bit. These are some of the examples of our technologies. This is a benchtop version. This is sponsored by NIBIB. This is sponsored by NHLBI. This is the newest one, which is in the form of a ring form factor that will be sponsored by NIBIB. We're actually running this study at Morehouse School of Medicine on African-American communities because of the limitations that I mentioned earlier to you. So one idea of capturing the physics part of the blood pressure is to understand the relations. We know that the blood pressure has correlations with blood volume, pulse transit time, and heart rate. And we can capture that from the bioimpedance. Some of these features correspond to the blood volume. This corresponds to the pulse transit time, which is the reflected pulse. When the pulse is traveling through the artery, it goes through the artery, it hits the end of it, and it comes back. As the pulse transit time goes up, the pulse is going to come back faster. So we can capture it here as well. And then the heart rate also has correlations with the blood pressure. So this is the idea that Khan had, one of my PhD students who just graduated. And the idea was to use the neural net. And neural net is really good. We use the conventional function, but neural net is really good in measuring the derivative. So we capture a bunch of derivatives based on these features. And then we use the Taylor series. And when we use the Taylor series, you can actually train the model to work really well. It turned out to actually be very effective with minimal amount of data, reducing the data by a factor of 15 and looking at all these different versions, electronic tattoos, rings, and then the benchtop version. The neural net ends up giving us fairly accurate results, and then it doesn't overfit, whereas the traditional model would overfit. The black here is the gold standard. The green is what we are capturing from our physics-informed neural net, and then the yellow is the conventional models. So this also motivates the connection to the sensor. One of the important aspects of this kind of work is to really understand the underlying physics. When I place the sensor on the skin, I want the sensor to stay at the same location. That motivates the notion of electronic tattoos and graphene. This is in conjunction with my existing work with Deji Akinwande at UT Austin, where now the model starts really understanding this, and the graphene is going to stay always at the same location. So once the model learns the physics, it's going to stick to it. Here is another example for Dr. Yu at Penn State. It has this wonderful technology called drawn on the skin that you can literally draw your sensors on the skin. How cool is that? So we talked a little bit about actionable information, end-to-end holistic view, and personalization. One of the things that I like to bring up is the abstraction that we build is the key. When we look at the first flight, Wright brothers, it was a 12-second flight. 12-second flight is not a significant flight, but that flight helped us to understand we can go from DC to Beijing. We can travel at the speed of 5 Mach, but that plane cannot go to the moon. So that's really what we are trying to do when we think about these paradigms. And then we need tools and tests to simulate and test. I'd like to acknowledge my sponsors, my wonderful collaborators. This is my team. My daughter, she's in the middle, future physics graduate students. We had a party a couple of weeks ago, and then I'm going to end with this quote from Dr. Sama. Thank you.
Wonderful. Thank you both for the great talks. At this point, I'd like to invite our speakers as well as our discussants, Drs. Edwin Khan and Raji Bhaskaran, up to the stage for some questions. And while they're getting settled, just a quick reminder, if you're on Zoom, please go ahead and enter your questions in the Q&A box. Great. Thank you. Dr. Khan, would you like to get us started with a question?
Let me ask a question for Changzhi first. Radar was developed for what you cannot see, right? So imaging is forever our competing part for radar. How do you see what you develop that can be either complementary or is better than imaging?
Yeah, great. Thank you for the great question. I think definitely I don't want to use the word of competing. Yeah, competition is always tough. I'll say it's more like a complementary. Radio frequency and image, camera image, you will see both have advantages and also limitations. So yesterday, I actually had some discussion with NIH researchers here, and I learned that camera is sort of unwanted sometimes, especially in home environment. If you want to monitor patients, privacy is a big issue. And with that being said, this is something radio frequency guys could sort of advertise or brag a little bit about, because for microwave radio frequency, you don't have that visual image. And if you look at the presentation I made today, a lot of things presented is sort of rough, and that is the limitation of RF and microwave. The resolution, especially angular resolution, is not comparable to image. It's just like today's car industry. If you buy a car, you're gonna see cameras, radar sensors, all types of sensors integrated. And people may argue that Tesla removed radar a few years ago, but the reality is Tesla is putting radar back because they realized without radar, there's going to be a lot of limitations. So I'll say collaboration, sensor fusion, integration would be a better approach from system point of view.
Dr. Bhaskaran?
Thanks both of you for really great presentations. I think there's some common themes that emerged. So I would like, either of you to answer this. You all presented some version of, bio-vital measurement that is non-traditional, or, what's upcoming in sensors, but also included some kind of data science, AI in the loop, to interpret this data, because it's a new modality, or maybe it's more continuous measurement. So you want to have some processing for interpretability. Can you comment on, as a community, can we develop some figure of merit on when we collect data on this large scale data, especially both continuous time and large population, whether we should have some figure of merit for how we judge these that are not only about the physics, which I really appreciate the physics informed neural net approach. But also if you do any data aggregation, the population based also figure of merit, right? And can we kind of lead that so that the commercial solutions like the optics, which you pointed out, both of you, the issues with optics, which is skin tone, BMI, many things that, are not really guaranteed to work as well. But maybe we can move the whole, ecosystem towards better solutions by putting out figure of merits.
So that's a great question. I love this. And I don't know if I have answer to that question. I would share this with you that my view on this technology development is not that they would actually be incorporated into wearables like this. It's really hard to convince these large companies to adopt these technologies for a small population. The view is you would have some sort of patch, for example, that you would wear the patients or individuals who can benefit from this. They would wear 2 nights every 2 weeks. And when they go under intervention, the patch would effectively help us to characterize some of those important hemodynamic parameters. It's going to be highly dependent on the direction. If you're trying to treat, hypertension, stress, or other disorders, baroreflex dysfunction, or those kind of things. But then, my general sense on that is the advantage that we have is we're trying to really, as opposed to starting with a group and going to phenotyping, we're trying to start from individuals and then build it bottom up. So
I'll add a little bit based on my personal experience. So I strongly agree with what Roosevelt said. My personal experience was when I was a PhD student engineer, I thought engineering problem is the toughest problem. And there is always FOM, figure of merit, to evaluate, quantify. But after I got married, after I got 3 kids, I learned that human beings are a lot more complex than engineering systems. That's totally different level. And that is why exactly I really appreciate the organizers to bring us engineers together with NIH researchers to learn different concerns, discuss the things from system point of view. So I really appreciate if we can get some figure of merit or quantifiable thing to evaluate from system point of view. But I believe in reality, there's a lot of research efforts needed to really come to that stage to clearly quantify, or maybe there is no way to absolutely quantify, but then we have to brainstorm together to figure out a way to really evaluate the system and find out what's the best systematic way to move the solution towards a better future.
Great. And we are running a little short on time, so I'm going to throw it back to Erin for any online questions that we may have.
Yes, there is one question from our virtual audience for Dr. Lee. And the question is there a future for synthetic aperture in portable radar?
Yeah, wonderful question. Thank you for the question. So synthetic aperture radar is amazing. Basically, what I presented here is very low level, low resolution system. You can see the image is not really that nice. The advantage of synthetic aperture is if you move the radar and grab data from different locations, you can potentially integrate all the data together. And effectively, you are looking at the target from a much bigger aperture. And in microwave and antenna engineering, with a bigger aperture, you get a much higher resolution. So this has already taken place. For example, Sandia Lab has done a lot of demonstration using synthetic aperture radar. You can clearly see the cities, see a lot of things on airplanes. But the future, I believe we can integrate this also in indoor environment to benefit human beings. Like if we can scan, for example, our room from different locations, maybe using a drone or some other platform, we can get high resolution results. Yeah, so synthetic aperture radar is something the radar community have been actively looking into.
Great. And Dr. Nye, question from the audience.
Hi, John Nye here from NIH. Thank you both speakers for exciting talks and the panelists as well. I have a question. I guess originally I was thinking for Dr. Lee, but perhaps everyone on the panel could address. Could you talk a little bit about the relative advantages, disadvantages, and different applications of, say, radar and infrared imaging, and specifically LiDAR?
Right. So I believe there are also researchers here using camera and LiDARs, like different, as we discussed a little bit, different systems definitely have their own pros and cons. So I think integration is something we can look into. On the other hand, complementary application scenarios. Like currently, radar, my feeling is radar is really lagging behind if we compare the development of other like optical technology. And there's a lot of things we can address.
And I'd like to add just one comment here. When we look at sort of these diverse group of technologies, radar can go deep, and that's really important. This standoff monitoring paradigm is extremely convenient and comfortable. That's the advantage. But the disadvantage, including some of the vision-based technologies, is when, for example, you're looking at the face and you're trying to focus on specific pixels to pick up the heart rate, you will have to have anchor points. They look at nose, they look at, the mouth to figure out where that pixel is and keep it at the same location. If you move, things are going to change. So there is also this push to move some of these technologies as close as possible. I mean, we have one of the leaders here, Dr. Rogers, who has done a lot of work in this area. Using even ultrasound on the skin in the form of electronic tattoo has been also one of the exciting things, because now there is the reference with respect to the body is no longer moving. And that would really push and help us to improve the fidelity of the signal and extract more important hemodynamic parameters.
Yeah, if I can add one comment is that I think following up on that, in general theme is that the more personalized you want, I think you want sound and light closer to the body. Something like radio frequency is good for context. So things like what's happening around in the room or around the environment, because it's 3D, right? But it doesn't have directionality. So think of it as like, I think radar for context, LiDAR for directional context, and then ultrasound audio as you come closer to the body from a human perspective, right? That may be one way to think about the overall thing. They all serve different functions.
I just want to quickly add for microwave and radio frequency, near field detection is also possible. Actually, Professor Ken and Professor Chow, they both have nice results like near field detection, which is not really absolutely in contact, but still very close to the subject.
Thank you.
Thank you. Okay, I believe we are at or perhaps past time. So thank you all very much. And I believe we are going to break now. Thank you.
Yes, thank you very much. The time is 10:51. We will be returning at 11 o'clock.
And welcome everyone back to our BBQS workshop, as we call it, and welcome to session 4. At this time, I would like to introduce my colleague, Dr. Ming Zan, as the moderator for session 4. Dr. Zan is a program officer at the NIMH and is team lead for the NIH Brain Initiative Informatics program, which supports the creation of data archives, establishment of data standards, and development of software tools, conducting secondary data analyses, and the Data Coordination and Artificial Intelligence Center of the Brain Behavior Quantification and Synchronization program. Prior to joining NIMH, Ming worked as the chief of bioinformatics at the Methodist Hospital Research Institute. He was also an adjunct professor at the University of Texas at Houston and was chief of the bioinformatics unit at the National Institute on Aging. His research included developing and applying computational and systems biology approaches in the cancer field. Please welcome Dr. Zan.
Thanks so much, Yvonne, and good evening. Good morning, everyone. So in this section, we're going to focus on sensor-related issues on data standardization, data archiving, and security and protection of the data. We have 4 speakers to make 3 presentations, followed by discussion. The first presentation is by Maria Palampini and Bruce Heck from IEEE. They're going to talk about brain sensor standards. The second presentation is by Dr. Satra Ghosh from MIT. He's going to talk about transformative potential and the challenges in open data and computation in neuroscience. The third presentation is by Dr. Oliver Rubel from Lawrence Berkeley National Laboratory. He's going to talk about behavior data standardization. Joining with us is also Dr. Greg Faber, the director of NIMH Office of Technology Development and Coordination. We will be discussing in the following discussion. So each presentation is going to have 12 minutes. Then the speaker is going to introduce the next speaker. So with that, let's start with the first presentation of Maria and Bruce.
Good morning, everyone. Really excited to be here at the NIH. I represent the healthcare and life science practice at the IEEE Standards Association, and I was delighted to see in these earlier presentations that a lot of the publications are coming through our various journals. But many of you are probably already very familiar with the IEEE, but really important that we focus on one core mission, and that's advancing technology for humanity. And the majority of our work, whether it be standards, technical activities, papers, how we move technologies forward, is always with that in mind. So with that, so again, we are the world's largest technology association. We are global. We have staff offices in 3 different continents. And obviously we have members in 160 plus countries. Many of you probably attended at least one of our technical conferences over time and have read many of our papers. So a little bit about the Standards Association. Obviously, we have many different paths to standards and different types of programs. A lot of the work that we do in the healthcare life science practice, and one of our chairs, Bruce Hecht, is here with us, and he'll talk about a little bit about some of the work we're doing, but really looking at how we can incubate ideas for potential standards. So some people come to us and say, hey, we have a great idea for a standard, and some people are like, we need to do a little more groundwork, we need a little more support. We need a sandbox. And so this is what we do in what we call industry connections. And this is really why we call it an incubator. Then we have our traditional standards, conformity assessment programs, the registries. There's just a whole plethora of opportunity. The big one in our newest tool belt is the open source. We do open source standards, and we have a very robust open essay platform. So the healthcare life science practice focuses on 3 major branches, of which is pharma biotech, clinical health, and global wellness. And essentially, the volunteers pretty much across the globe in these 3 areas really look at how we're going to drive adoption and trust in these technologies and these applications across the healthcare value chain. So we're looking everywhere from bench to bedside, which is healthcare delivery. So today we're just going to talk about, we only have 12 minutes. We can talk about a case study that we've been working on. I could take a whole day for it, but we're going to try to just get you the highlights on one or more recent open source standards, 1752.1. We think this is an opportunity that fits into a lot of the discussions we're talking about today. And we'll have Bruce talk a little bit more about criteria that we're talking about and potentially the applications and end user impact. So 1752.1 is actually the part of a family of standards for mobile health data. It's an open source standard. And the one that was published is on representation of metadata, sleep, and physical activity measures. This is what we call the base standard. And then from there, we went into the next therapeutic area for the wearable. And I'm going to show you what the metadata and that kind of thing looks like. The standard for cardiovascular, respiratory, and metabolic measures. So there is a baseline schema here from this particular standard that now can be totally adopted or manipulated, for lack of a better term, to say, okay, we have cardiovascular application, we can have brain sensor application, we can have mental health, digital mental health. So this schema is a very strong baseline for the wearables. So this is courtesy of Open mHealth. Open mHealth actually chairs the 1752 family of standards. And it really talks about the idea of the metadata landscape. So we look at wearables, regardless if they're in body, on body, or around the body, and talking about how the data stream pretty much goes from cloud, and then it can go into EHR or eventually into clinical trial management system. The idea of 1752.1, so I'm going to show you the book. That's me. Here we go. So this was sort of like a case pilot that we've been working on. The idea is to look at before the standard was applied and after the standard is applied. So we take the use case of sleep, right? So pretty much the question is how long do you sleep? And so there's 4 different ways we can quantify the time or duration of sleep, right? So we look at sleep duration, total sleep, time sleep, sleep time. Which one is right? Well, in this case, all these different variations on how these things are calculated just create a problem when we're trying to pull this data in for research. It's just a simple semantic problem. So what the team did was pretty much through the development of the standard, is basically they just created a mapping of these terms, right, to come to a point that say total amount of time spent asleep. This is the metadata coming from these wearables is now streamlined. So they took out, the semantics are clear and the metadata is complete. And basically this allows this data to be now used for clinical research, right? So I'm making this very simple, right? Because the data comes from the wearable, goes through an aggregator, and then it gets into the clinical research realm. But the important key here is the idea that we basically streamline the semantics of just duration of sleep, right? And that was the point of the standard. And now this can be translated, let me show you. So this is the schema, which is available on GitHub. It's open source. Basically, this is the schema that we can follow now for your cardiovascular wearables, right? Or other therapeutic application wearables, regardless of on-body location. So this is really what I call, this is the way around the wearable situation when we talk about interoperability of the data, or how we're going to port the data out. How can we try to get the data out of a wearable from just monitoring into clinical research mode? So basically some of the benefits, we're really going to, the big thing is the reduction of data friction, which was a really big one. It's the idea now that we can take also commercial health wearables and try to give them a platform to sort of migrate into the clinical research space. This is also a standard that we've talked to the FDA about. It's not written into policy, but it's recognized. So if a wearable or the data that's being used for research says it's following 1752.1, which is the published standard, it will be recognized and accepted in submission review. But I think the most important thing here is that the data collected from various devices, right? Regardless who's the manufacturer, regardless of the proprietary algorithms embedded within them, it'll have the same measure, and it'll be and it can be pulled for analysis. And this is like really, really critical towards moving wearables out of this current siloed category. So with that, I'd like to bring up Bruce to talk about some of the key considerations for the standardization.
Great. Thank you very much, Maria. And I'd like to thank Min for hosting this session, and of course to Dana and Holly and Yvonne for having us here in this wonderful location. As you've heard, there are many questions that we're seeking to answer, and we're looking for ways to do collaboration. So to build on what Maria has shown you about how the use of standards could be developed, and how we're inviting everyone that's here today in the room and those also that are online to help put forward what would be standards that would be helpful in realizing the understanding of the brain, as well as applications into clinical practice. So one example could be if there's a combination, and this builds on one of the key 3 themes of the last 2 days, which is multimodal. So what if there are different types of sensor modalities that are being collected about a particular question of interest? And this one here that's being shown could involve temperature, pH levels, and pressure monitoring. This could have a variety of applications. For example, if there's a pressure buildup inside the brain, either due to a disease condition or possibly due to concussion or other types of traumatic brain injury. And so in this particular example, there would be a desire to combine those 3 sensor modalities. And then, of course, what we want is not only the data, but how it will be applied on its use case. And we might be considering the compatibility of the data, how interoperability would occur both in the collection as well as how it's being shared through electronic medical records or other systems involved with patients. Issues of quality. Sometimes in the systems engineering world, we call these the ilities, like reliability, quality, and those would also include safety and security and privacy of the information. And how does this affect with ethics, which has been another recurring theme of the past 2 days. Those questions are both about respecting the individual, but also about how we can gain collective information that helps make our society stronger and gives us the capacities to improve health for our communities. And then what happens if we're introducing other measures? For example, EEG is one of the most common ways that we have access without being invasive to the brain. And if we want to collect that information, which might have a lot more time, specificity to it, how can we use the design of the standard to help make that work? So as you've seen, this 1752 series has in it, intention. So what would it be? In the prior example that Maria showed, the question was involving sleep. And so there was an abstraction there about what might be important about sleep. In this particular example that's being illustrated, depending on the use case or the application, there could be different ways that the abstractions might be defined. So in addition to that, we wanted to share this point about brain-machine interface. So there is an initiative related Neurotechnologies for brain-machine interface standards, and this is taking the form of a roadmap. Maybe the second of the themes that I want to share today, building as what we're just talking about intermodal, is this question of roadmaps. So as everyone in this room is part of the development of technology, we know that what's exciting about technology is not necessarily what it can do today, but how does it evolve over time? And to get that evolution also requires investment, both of resources, which we thank those who provide financial resources, but also time and learning. And as we're each seeking to advance the state of knowledge, as well as to inculcate, to bring forward the capacities of our researchers, our engineers, our scientists, our practitioners, and our caregivers, and also ourselves, which has been a theme, we're seeking to find out, well, how does that change over time? And overall, there can be acceleration in the sense that what we learn in one generation of technology could require substantial amounts of investment. But as we get that learning, that then sets the stage for the next cycle. And if we can continue to see widespread adoption and use of these technologies, then can produce a virtuous cycle, which is really what we're seeking. Because if we're all progressing in linear time, we will have a difficult challenge to get to the need, to fill the needs that we see that are so important in those that we love and that are in our world. And so that idea of roadmaps, which is more generally being done across the IEEE with the roadmaps committee and with the future directions committee. And so here's one example, and we invite you to get involved with this with us as well. Thank you. So I just wanted to sum up. You've got our contact information here, myself as well as Maria. We've got global programs. As you mentioned, I'll just add one more plug for one of the programs that is currently underway. That's the Industry Connections Program for Telehealth. So we're looking at what are the technologies as well as what are the application challenges that are involved in delivering telehealth and a hospital to the home and other ways that people can get the benefit of health wherever they are. So with that, I'd like to thank everyone, and I look forward to the conversation. It's my pleasure to introduce next Dr. Satya Ghosh, who's at MIT and the McGovern Institute, and also with Harvard Medical School.
While this comes up, it's been a pleasure to be here. I've learned so much over the last day and a half of all the things that have been presented. I'm really excited. And for those of you who have spoken to, I want to put all those sensors on myself. So I'm looking forward to getting those sensors. And I'm happy to be your participant in progress. I consent to my data being shared openly as you do this. I'm going to try and tell you a few stories today. It's a little bit about my journey, but where we are today at the intersection of neuroscience, neurotechnologies, and neuroinformatics. As we see this evolution of the world, we've heard a lot of sensors talk over the last year and a half. They generate data. What do we do with it? How do we work with it? How do we put things together? So this is a slide I've been using for a little bit of time, kind of inspired by Randall Munroe, creator of XKCD, with this hypothetical question. what if all data in the world were instantly accessible? What would happen to the society if that were the case? And I would say, on the current moment, probably mostly useless. However, this gives me an opportunity to bring up something like this. Right? We are in the age of AI and ML, doing a lot of things. So we have a lot of data, and keep working on it, and then keep working on it further. But hopefully we can change this world towards something a little better. But today, I'm going to talk about kind of two different dimensions of this. I'm going to first look at infrastructure, standards, computing, the ecosystem of these tools and data that we live in, the training that's needed around it, but through the lens of a few other dimensions. The first thing is availability. And this cuts across all of these things. It's not just data. We often talk about data as being the thing that we need to make available. But it's about standards. We just heard an excellent presentation from Maria and Bruce, kind of talking about the evolution of standards. Computing, it's changing on a daily basis. We want to be able to tap into what are the dimensions that intersect, what's available. Same thing with ecosystems and training. How do we become parts of communities that can evolve these things? There was an open call that Bruce laid out for helping with some of the standards development work. Second thing is discoverability. And this is something I've realized, as our group has spent some time on it. Often we live in echo chambers and it's hard to find things. They simply are situated. We have all the search engines of the world, but it's hard to find things unless you're in the right group at the right time. Finally, the third dimension of this space would be usability. We're putting things out there, and we want it, right? I'm very much an open source. We want things out there. But that doesn't mean that all of it is usable in the same way at the same time. We have to kind of think about what usability means, and further, what somebody might find as usable and not usable. How do we get that kind of information out there in a process where we can shorten the feedback loops in our systems? So let me start with infrastructure. One of the hats I wear is that we maintain one of these Brain Initiative supported data archives called DANDY. It stands for Distributed Archives for Neurophysiology Data Integration. But we kind of call it not just an archive, but as a collaboration space, because part of our goal is to help change some of the culture around how we think about data and compute together. So this archive has grown just in about 3 years to storing about 0.5 petabyte of data. And that's just the tip of that iceberg. If all of the data were instantly accessible, this would be much, much, much larger. And this is compressed data for those of you who are considering we don't use standards or other things, and standardized data, and streaming data. It's a fairly modern archive. You can get to this data programmatically, you can push and interact with this programmatically, and you have compute resources that sit next to the archive that you can use to do work on this archive. However, we sample only a small space, what we might call the neuroscience. And the good news is that the Brain Initiative and other resources are coming out that provide many different avenues of getting at different types of data in the space. So in the red box are all the Brain Initiative supported data archives. But in addition to that, there are a bunch of other archives. Actually, I didn't put OpenNeuro in that box, but OpenNeuro is also a Brain Initiative supported data archive. But there are biobanks being created both in other consortia and cohorts around the world, which are giving access to a whole lot of data that's coming online. So we have an opportunity, an incredible amount of resources and participant effort is coming in towards producing these data. Let's make use of it. Let's make them as good as possible so that we can do the kinds of science we want to do. Let's bring in these new sensor technology data sets into this space. Let's see how they would be used by other people. This brings me to the second component, standards. Now, we just heard about a process of getting at standards. I'm going to give a little bit of a story over here. So one of the types of data we've been asked to store in the archive is light sheet imaging of human brain tissue that has been stained through different proteomic markers. And this data set alone is about 70% of the archive right now. It's a lot of data. It's a whole human hemisphere, actually 60% of it right now. So I expect just this alone to scale up to about 0.5 petabyte when it's said and done. And that's, again, just the very tip of the next generation of data that will be produced by some of these consortial initiatives. Why do I talk about standards in relation to this? Well, partly because when you think about standards, you think about a bunch of different elements: data formats, data dictionaries, data identifiers, unique identifiers and definitions around the data formats. You have to describe data, right? And that's challenging because if something does not exist, we use English, our human communication language, to describe these things. And as we all know, we are great at communicating. Right? We all understand each other perfectly all the time. So hopefully we'll do a little better with kind of digital representation of information. And often we find that there are no consensus data standards. So this brings me back to Randall Munroe. Standards proliferate. Well, there were 14 competing standards. Oh, ridiculous. We need to develop one universal standard. Well, now there are 15 competing standards. So we tried to do our best to not comply with Randall's thing, and we brought two communities together, the microscopy community and the brain imaging community. Both had been describing some of these things in their own terms, in their own spaces. And we were able to bring these communities together. So instead of creating the 15th standard, we tried to merge maybe the 14th and 7th standards in that space. And that allowed us to bring a bunch of people who don't normally talk to each other together. So there was a notion of getting a community of people cross exchanging information as well, which I think is important as we get into the complexity of neuroscience, as we look at the different kinds of information that are being generated. We need more people conversing and talking to each other about what information they're exchanging. Well, that gets us into kind of standardized format. Let's move on to the third component, computing. We've lived in a world where we think of computing as the data exists, we pull it down, compute with it. Let's start pulling more data. This is the evolution of the NeuroPixels probe. For those of you who are doing neurophysiology, will have seen some of these things. And it used to generate about 1 terabyte of data in 13 hours of recording. The next generation probe increased the space of channels significantly. It's an order of magnitude increase. So that changes the dynamics of data generation. The one that's in development, I've been told, will generate about 0.5 petabyte of data for a grad student or postdoc or experiment. That changes the dynamics of computing with these things. It changes thinking about where that data might live and how that data needs to move. So this is an example at different speeds of connection, how long it takes to move data from one place to another. And different institutions, different places where data are being generated will, at least in the near future, have some of these limitations that come into play. The other side of this is computing itself. We're living in a world where AI and ML are changing at a very rapid rate. The training of GPT-3 alone is a significant burden on computing talent. However, some of these numbers below, so in terms of this scale, we also have to do multiplications on some of these things. But we have to think about computation strategies and what we might do as a community to reduce computation as these data sets and other things grow. And one way to think about this is through this lens of what we call data levels. So this came out of the BICCN work, thinking about data levels as raw data, validated data, linked data, featured data, and integrated data. Each of these requires computational processes that the community needs to come together to agree on or assemble a set of processes. Because often those featured data sets are significantly smaller, but that requires agreement in the community in thinking about what we bring together. For example, in the neurophys community, do we agree on spike sorting techniques? Can we agree on spike sorting techniques? I don't know the answer here, but I encourage the community to kind of come to terms with what do we do to consolidate computation so that we can reduce the burden of running the same models over and over again in different ways. So this brings me to ecosystems. The BICCN ecosystem was a wonderful ecosystem of getting archives, computational folks, and scientists together to create this ecosystem of delivering standards, create archives that can house the data and connect the data. The similar ecosystems, you'll hear a little bit more from Oliver in the next talk about the Neurodata Without Borders ecosystem that works on neurophysiology. I've been fortunate enough to be part of the BIDS community, part of this NIPREPS ecosystem, which is trying to consolidate neuroimaging data alongside behavioral and other data in a common way. We also have to think about our participants, right? That comments contribute data in this case. And we've all heard the term fair, probably, but we often don't hear about the term care. And this is about understanding human consent or participant consent, that other participants are contributing data. Let's make the most of it as it comes together in these archives and communities. One of the things that we did in the human brain consent process is to consolidate how we even approach the consenting process across different studies. So the open brain consent is one of these things that allows us to create documents that different institutions can use even to get data in. Because as we heard yesterday, the sensor developed in the 19th century isn't how we are using the sensor today. Each of these data elements or data bits that we store are going to be similar. We don't know how this will be used in the future. So let's think about what that means from our participants and contributors today. This brings me to kind of the last few points of this talk, training. The world is expanding. We've already talked about standards. We talk about grad students, postdocs, research staff, professors trying to put data into these things. It requires a lot of different elements, and most of our programs are not quite there to go across all of these elements. And this is just in kind of standardization metadata space. The evolution of LLMs, the change happening almost on a monthly basis in some of these spaces. How do we bring these communities together in terms of training and intersection which is required? So there are many challenges, we call them opportunities, right? Every challenge is an opportunity. The challenges around curation, standards, and education. Our domains are evolving. We have to evolve with it. There's data and computational provenance. We need to make meaning of the data when this appears 10 years from now or 20 years from now. We need sustainability and governance. Right now, we're storing everything, but as the time will soon come where we'll need to decide what to keep when we often don't know what to keep. Transparency and ethics are one of those elements where the data comes from complex systems, come from participants, and we need to understand how that is transparently done in a world that is complex. I'll end with this slide. This is a figure I used to use almost about 10 years back. This is NetApp, the storage company, thinking about sources of data. They were thinking far ahead at that point in time in terms of how much data the human body was going to generate. This couples with our kind of research program and portfolio in our group. Want to integrate different sources of information, couple it through various kinds of technologies, but work together with clinicians, caregivers, patients in a closed loop system. And we wanted to shorten these loops as much as possible and be transparent. So with that, I want to thank you for your attention. Happy to invite Oliver to the stage.
Guys are coming up. So my name is Oliver Rubel. I'm from Lawrence Berkeley National Laboratory. My background is broadly in data science and data understanding. So anything along the data pipeline, from generating visualization tools, analysis algorithms, to data standards. In the context of the Brain Initiative, one of our main projects is on Neurodata Without Borders. WB is a data standard for neurophysiology data that we're creating. So what I want to do today in my talk is really more broadly speak about challenges and opportunities in data understanding. And what I'm going to do in my talk is talk through some of the roles and the challenges that we have in data in data standardization. And I'll also talk about the opportunities and the requirements that arise from. So with that, let's dive in. So like I said, I'm going to talk about roles and challenges and requirements and opportunities. And so throughout my talk, you will see me use these kind of orange and blue markers to demark, as I'm referring to a role and a challenge, and then in blue, the requirements and opportunities that arise from it. So first of all, why do we need data standards? And so one main role that data standards have is that they allow us to efficiently use and share data and to enable scientists to collaborate through data. And so that is, data standards are really a critical conduit that facilitates the flow of data throughout the data lifecycle, from acquisition to processing, analysis, to sharing and publication, and ultimately data reuse. And then also to facilitate the integration of data and software across these different phases of the data lifecycle. And so scientific...
Pardon the interruption. We're having problems hearing on Zoom.
Okay. Does that work if I lean down?
Yes, thank you.
All right. All right, I will make myself smaller. And so, okay, so where was I? Okay, and so scientific data standard technologies are really at the heart of the data lifecycle. And what this means is that as scientific data standards goes, we need to support and integrate with the needs of and technologies across all the phases of this data lifecycle. And so we need to work with, not compete with, existing and emerging technologies. But it also means from a data user perspective, or as an experimenter, we really need to think of data standards as technologies that we use from the beginning and throughout our experiments, not just as technologies that we need to then finally publish the data. It's really something we need to consider throughout the entire experimental process. A key challenge in the development of data standards for neuroscience is really in the diversity of neuroscience experiments, which involve a wide variety of species and tasks, data modalities, devices, and brain areas. And so in addition, there's also then the high rate of technological and methodological innovation that we're seeing in the community. And so data standards for behavior need to be both comprehensive and extensible. So as an example, in the NWB data standard for neurophysiology, we cover a broad range of data modalities, from recordings of the neural activity through electrical and optical physiology, to metadata about the acquisition and the subjects, to information about the design of the experiment itself, whether that is the presentations of stimuli that we did to our subjects, the structure in terms of trials of the experiment, descriptions of the tasks that were performed during the experiment, and then ultimately also recordings of information about the behavior itself, whether it's through motion tracking or audio, that are directly associated with the neural recording data. And so as an analogy, think of data standards as a language. And much like natural language evolves with the concepts of societies that use them, we need more than just very rigid data formats, but we require flexible data languages that enable us to communicate via data. And so scientific data standards are really the language we use to communicate through data. And as such, these standards need to be comprehensive. They need to provide us with broad coverage of an experiment's raw and processed data. Our standards need to be extensible to support the evolution of these data languages with the changing needs of the communities. They also need to be stable. That means they need to provide us with standardized core concepts that we can establish and use throughout the life cycle of our data. They also need to be accessible to the community. They need to be easy to use. And then finally, they need to be reliable. We need to be able to have these technologies stable enough that we can use them in our regular day-to-day production, as well as then preserve the data in the long term. And so in the context of brain behavior, a key challenge here is also that in order to begin to understand how the brain creates behavior, we need to be able to relate and integrate data from multiple modalities. We have heard this throughout this workshop many times. And so, for example, we need to relate the neural activity that we report to the stimuli that were presented during experiments, as well as then the behavior that our subjects showed during the experiment. And so we do not just need standards for individual modalities, but we really need integrated data standards to allow us to store and relate raw and processed data from a wide range of data modalities. So as an example, here in the figure, we see a pipeline where we use NWB to store data from electrical and optical physiology, which is recorded simultaneously. And then we also store the processed results from spike sorting and RI detection in the same data file, which in turn allows us to relate that data in analysis easily so we can look at both the optical and the electrical signals in a coherent structure. One of the key challenges in the development of data standards, in particular for neuroscience, is the diversity of the stakeholders and the requirements at all the different phases of the data lifecycle. So a key aspect that has allowed us to really manage this diversity of requirements and really the diversity of discussions that arise from this is that already early on when we developed NWB, we identified and outlined the main components that we need to define the data standard. And so, for example, when we just want to create data standards, it's not just about how we want to organize the data. We also need to discuss how we want to store the data. We also need to talk about how we actually want to use the data as end users. And so we need to be able to have these discussions and have these different aspects of the data standardization process evolve. Right? As we move data from our local laptops to the cloud, how we store data needs to change. But the data standard itself still needs to be able to remain stable in these kind of situations. And so a key strategy then to manage this diversity of stakeholders and needs is to use modular designs where we identify and define and insulate all these different areas of concern and then define standardized interfaces between them to integrate across these components. And this is really critical because it allows us to frame the discussions with stakeholders, as well as to allow this data standard ecosystem to evolve with the needs of the communities. So for example, as we move data to different systems, again, we can adjust how we store the data without actually affecting how we organize the data and how we use the data. But data standards are only one piece of the puzzle. To really take advantage of the promise of data standards and to allow us to share and reuse data and communicate and collaborate with each other, we need more than just standards, but we need an integrated software ecosystem that spans the entire data lifecycle and builds around these data standards. For example, in the context of NWB, our core software stack alone consists of more than a dozen different software tools, such as APIs to read and write the data, tools to convert and inspect data, tools to support the extension of the standard to allow users to integrate new data types with the data standard and other data modeling technologies. And then on top of all this software that we have on the core, there's a growing collection of community tools for visualization, analysis, data management, data sharing, that sits around this, that is created and maintained by the community. And it's really this access that you get to new capabilities with data standards that provides a broad incentive for users to adopt standards and that adds value to our scientific endeavor. In the context of studying brain behavior, a key challenge that we have with regard to the software ecosystem is that we have still large gaps in the ecosystem for moving from designing experiment to actually sharing the data. Right? And this begins at the very beginning as we design tasks for subjects to probe behavior. And so while there's many tools to design behavioral experiments, they really focus on how we program the controls for an experiment. However, we lack standards to really formally describe the tasks that are being performed. So the Beetle behavioral task description language is a first step in the direction by allowing us to abstract the description of tasks from the hardware design. But it's really just the first step. We need much more rigorous ways to define tasks in a way that they're both programmatically interpretable as well as human readable. And then importantly, once we have defined tasks, we need ways to evaluate these tasks that we define for subjects before we actually execute them in an experiment. We currently do not have tools to simulate task designs and to subsequently evaluate them before we put them in practice. And then another key aspect is that once we have executed experiments, we currently lack standards to publish tasks in a structured way. Most of the information about how tasks are designed is contained in free-form text and method sections, which is insufficient to really let others recreate and reuse data and reproduce the results. Using, again, language as an analogy, data standards alone, as Satra also pointed out, are not sufficient to fully define a data language. Right? Simplified speaking, you can think of data standards such as NWB or BIDS as the syntax and the morphology of our language. They define the structures and the organization for exchanging neuroscience data. But we then also need to define the diction, meaning the terms that we use in our data. And that's what we need control sets of terms for. And then to define the meaning of the term, meaning the semantics of our language, we then need large collections of external resources, such as integration with brain atlases, ontologies broadly for species, gene function, taxonomies, and so on, as well as integration with persistent digital identifiers, such as ORCIDs, DOIs, RID, and so on. And so data standards, control term sets, and external resources are really an essential and synergistic pieces of this data standardization ecosystem that we need to address to really move to a world where we can share and reuse data freely. A key part of that is then that in addition to storing data, we need to be able to link data across different sources and with external resources. So for example, just very simply, right, if I enter that I used a mouse as my subject, we need to be able to link this term mouse to its description in the taxonomies that define our species. Or if I list myself as the experimenter that generated data, I need to be able to link that name to its unique identifier via ORCID to make sure we can identify who the actual experimenter is, because there may be many experimenters with the same name in this world. Or when we define locations of the brain where we had a probe, we need to be able to link those terms that we use to describe these locations to the appropriate brain atlases, really allow us to integrate and reuse. And then finally, beyond all these various technical and methodological challenges that I touched on, a key challenge in data standardization that we need to address is that we need to invest in overcoming the sociological challenges and to help scientists overcome the energy barrier for adopting data standards. And so this requires a broad range of strategies, from the incentives through funding and data governance guidelines that help us climb this hill of data standardization, to training, guidance, outreach, and support to help lower the barriers of adoption, to make it easier for scientists to adopt standards. And then also carrots in the form of access to unique capabilities, such as analysis and visualization tools that will help us do better science. And with that, I believe I'm at time, and we'll do a discussion with Greg and others.
That's very good. Three presentations. Thanks to the speaker very much. Then we have speakers and Dr. Doppler here.
Well, while all the speakers get settled, I do want to thank them all for a series of quite interesting talks. At least that was my takeaway from this. So we do not have an enormous amount of time, which is a shame, because I think I could probably ask a series of questions that would last for another hour or so. What I do want to really focus on, and I think I want to ask this question of all of the speakers, it has to do with the proliferation of standards. And I know of two pathways to go from lots of standards to a standard, right? One occurs fairly frequently, and it is that the funders or the journals or the FDA or somebody defines a standard and says, if you want funding from us, if you want to publish papers with us, if you want to submit something to us, here's how it's going to come in, and that becomes the standard for the field. Nothing wrong with that necessarily, but I know of one other case which involved the creation of the DICOM standard, which feels very much more like a community consensus that actually worked and got to a standard that everyone lives with. Now, I wasn't part of those discussions, so perhaps it's not as clean as I'm making it seem. But my question for all of you is really twofold. First, where do you think we are today in terms of standards for sensors and perhaps personal tracking devices, which I think are going to be a critical component of the work that's going to be going on? Are we still in the development stage where it's too early to really think seriously? Are we too late in that there's a lot of different companies out there that have developed their own idiosyncratic standards internally, and none of them are sharing with anyone? And then part two of the question is, and it depends on your answer to part one, but what's the path forward from where we are to where we need to be to allow the research community writ large to use and reuse the data coming out of these devices? So I don't know who wants to start. Maybe no one wants to start, but anyone want to take a crack at those questions?
All right, I'll go first. Okay, these are actually very good questions, but the second point that you had brought up in your early, with regards to consensus-driven standards, these are exactly the types of standards that we develop at the IEEE Standards Association and like SDOs around the world. The idea is to bring the industry participants together to build consensus and bring the standard forward, and not be beholden to, a particular platform or, particular framework or process. The idea is they build it together. It's neutral and it's agnostic and should be representative of the voices that are going to be impacted by the standard. So by the voices, I mean the clinical side, the technology side, the regulator side, and patients, of course, is something we have to keep in our purview. But the point about the things about sensors and technologies, the reality is we all seeing how rapidly this is a growing market, innovation, the integration of AI, machine learning, AI at the edge. This is unbelievably awesome in a good way because it presents so many benefits for us. But at the same time, the challenges that come with them haven't gone away. And that's the reality of the interoperability, the idea of compatibility, the idea of the sensor in itself. We're talking about the hardware, right? Let's not forget all the little intricacies of chips. And then the software around them, and the data transmission, and the data security, and the privacy, and the ethical governance. All these challenges are still there from the first sensor that was put on, your arm like a couple years ago. So I think we are early stage. The real core question is for everybody to think about is like, what's going to change? Where do we really need the standard development, and not to confuse it with policy, right? From a standard development perspective, we're here to say the market has come together to address a problem and so that we can actually open the door to innovation. And from a policy perspective, they are definitely part of the process to understand what that standard means. So I think it's early, but I think it's necessary, and hopefully we'll see obviously more important standards coming out.
Thanks, Maria. If I could build, I think, on what's really exciting about that, what you saw, in the talks yesterday and today. I wanted to highlight my own field with Dr. Andre Schkal about accelerometers. So there is something that was a measurement, that people were interested in, but the technology really changed by the orders of magnitude. So 1 million times more performance for cost.
So I think, the standards are themselves a kind of a technology. It's a technology of the way that people work together. So we might want to consider, what are the figures of merit? And are we really going to seeing, or what could we do to get 1 million times improvement? Similarly in the genomics field, of course, the Human Genome Project, which was an enormous amount of work. When it first started, people reported on it and said, look, you've only done 0.000, of it in the first year. So this project's obviously never going to be completed, but it's an exponential technology that changes over time. And that's really what we rely on. I wanted to point out also, in Satya's talk about open source, and Oliver's as well, like the example of Arduino. So there's something that if you want to use a piece of sensor technology, it comes with it compatible information that you can use and get it to work right away. But really where this is going, I think, and maybe this is where you could jump in, Satya, is it's not just about the collecting of the data, but it's making the data computable. So what are you going to do with it? And you can't do it all by hand with a single individual. So maybe there's an opportunity that you wanted to comment on.
Sure. I'll actually use a term I think Maria used in her talk, reduce friction. I think that's one of the challenges. Standards are not developed in a void. They're intended for a purpose. And right now, I think there's a gap between the standards development part and the intended use part. And that's where I think that gap could be filled by the right people and the right communities to come together and say, it's not just a standard in the void. There's benefits to the stakeholders when developing the standard.
To speak to your also question of timeliness, right? Data standards always are starting from chaos, right? Because initially when we create new technologies, everybody will create their own way of storing the data. And then as we come together, data standards are ways of consolidating that structure. One key aspect I think that we have heard here is also, this idea of multiple modalities. And we still have a tendency often to think of standards as I need to develop a standard for a modality, rather than how can we bridge across multiple standards and modalities, right? And I think we also have a great opportunity here in the NIH Brain Initiative to start talking about how we go across, neurophysiology to behavioral sensors, and how we cross these. And we're all scientists. All we want to do is talk about what we do, and so it's not that we want to create many different standards, but that is just the model that has existed for a long time. But for example, we're also working with BIDs on extension modalities to integrate NAV with BIDs. But I think that there needs to be much more strategic efforts to really say, how can we bring all these different areas together and start defining how we can work effectively across these different standards? Because yes, we need different standards, but we also need guidance for users, how they can utilize these standards effectively to work across all these different technologies.
Yeah, this is a wonderful conversation. In the interest of time, we're going to take questions from audience. We start from a virtual audience. Ori, you have a question there? Yeah.
There are no questions from the virtual audience at this time.
Okay, so then take question from the floor. Yeah.
Thank you so much. Who's Jafari from Texas A&M. So my question pertains to data standards. And in many instances, when we run studies, the investigator knows about all the details. But when you make the data available, AI algorithms and those who are building AI algorithms know very little about the context around the experiments. Blood pressure, motion artifact is important, posture is important. As a part of my obligation to NIH, I always make my data available as a part of our publications after we have done the vetting. And the kind of questions that I receive from researchers are fairly interesting. NIH has been doing also quite a bit of work and leading efforts on bridge to AI, which is what does it take to get to AI? So my question is, the metadata, the context is highly irregular. It's very much dependent on the study. I always struggle how you could define a standard how do you define labels, the probabilistic nature? What should be the temporal resolution? Do you think if there is a solution to that?
Any of you could jump in that question.
So the thing I would say there is that, data standards or developing of standards is a means of finding consensus, right? And so as we talk about data standards, there's always going to be a gradual development where, let's say, on the simplest case, we agree on how do we store a time series, right? Whether you have an electrical signal or a radar signal, they're both time series. How can we define how we store those series? So at least then I can start interpreting a data, right? And so you gradually move more and more to a more complete picture. But there's always going to be a thin layer on top that basically says, okay, this is not standardized yet. And that's why I mentioned in my talk also, extensions are fundamental because there are common components that we have agreed upon, and then there's all these new pieces that we have not agreed upon yet. And we need to provide you the means to communicate not just the parts that we have agreed upon, but then also include all that additional information that is specific for your experiment. But if we can move step by step to a consensus, at least we're getting closer and closer to being able to talk with each other.
Great. I take second question from that side.
So this is, I guess, more of a comment than a question, but I will finalize the question. But so my comment is, IEEE, in addition to having, just these technical standards, it also has these socio-technical standards. So as we're thinking of these multimodal sensors, I think it's important for us as a community to think, what are the societal implications of all these sensors that we are thinking about? So I think, bringing that community, in addition to just the technical standards, but also bringing people from the socio-technical standards, like the 7000 series, they would be a relevant component of these discussions. And my question would be, what would be specific challenges of introducing the care framework that Sergey mentioned in trying to create standards for sensors technology?
Right, anyone?
I can briefly take on the care framework. So I think part of the care framework is about engaging stakeholders in the conversation. So those standards, we often build technical standards with stakeholders. We think through the engineering lenses, the science lenses, not necessarily through the stakeholder lenses. When we think about IRB and other kinds of committees, there's always a participant involved in that kind of community. And I think that's the kind of thing that might bring some of those care elements in the development of standards. So I think it's about more diverse representation in the development of standards that we have to work towards.
Great. We take a last question because of that time.
Maybe we'll have time for two because it's just a brief question. During that very beginning of the process, and I'm asking that for the IEEE process as well as Neuro Data Without Borders, as well as Dandy, where you're just working out the semantics and coming together on definitions. How many perspectives were in the room? Less than 3, more than 10? And how much time did it take to do the first step? Like Oliver, how much time did it take for people to agree on what a time series was? We're just trying to get an idea of the time scale of building the foundation of a shared database when it comes to semantics.
Anyone take this question?
Well, I mean, so NWB in software, right, started even before I joined, right? I've been involved with a standard now for nearly 10 years. And so it's, in terms of number of perspectives, right, it starts off with really identifying who are the stakeholders and bringing them all in the room. And so that means you're not just going to have 3, 4 perspectives, but we talk typically, you need to have at least, let's say, 20 people in a room to start off with. Right. And then it comes down to identifying what are the different pieces, right? Because then we can have a focused discussion. It's not all fundamentally that hard to define it, how should we store a time series? But we need to clearly define that question and what we're talking about. So we're not ending up in discussions of, data storage technologies and whatever not. Let's define what a time series is, right? And so when we can focus our discussions, then we can gradually build it out. So
I think it's an interesting question because we get a question all the time on this, like how long does it take to develop a standard? So there are different tracks to it. And what I'd say is we'll call it the accelerated track, which is when you come in with a group of like-minded individuals and they're diversified, meaning they represent different areas of the community. You kind of come in already with like this groundwork for the idea, and then you bring in other individuals who understand what like the next step is. I've seen this particular working group that they did on the sleep study. They were about 40 participants from start to finish. I'm going to say average because they might have started out at 60 and then dropped and came up, through this life cycle. I believe they took about 18 months to actually vote and have the standard published. This second standard on the cardiovascular application is moving at faster speed because we have the baseline schema. So now really what they're focusing on is the therapeutic use case and making the schema work for that. And so subsequent standards in those therapeutic families will probably accelerate just as fast. And the cardiovascular group is hovering about 25 average participants. So they have the baseline from the first one. Now they've brought in the clinical researchers and the clinicians on the cardiovascular side to obviously put the therapeutic application to fit those terminologies and that kind of thing.
Great. So we concluded this part of our workshop, and thank speakers and Dr. Faber for the excellent presentation and the discussion.
So I want to welcome everybody back from lunch. So the next session that we're going to have is session 5, which is featured experiments in development of computational models. I would like to introduce our moderator for this particular session, which is Dr. Holly Moore. Just briefly, Holly Moore oversees a portfolio focused on preclinical and basic studies and non-human models on neuromechanisms underlying cognitive, affective, and behavioral processes that mediate the risk and maintenance of compulsive drug taking and dependence. And her background is in behavioral neuroscience and translational research using primary rodent model systems to probe neural circuit function relevant to psychiatric disease. So I would like to invite her up here as she's a perfect moderator for the next session.
Thanks very much. Our next session, as you can see, is called Featured Experiments and Development of Computational Models. The idea here was, as our last session, to put some end users up here and computational modelers up here on stage to talk about their use of everything you've heard about so far in the meeting. We have as our first speaker, Nico Hastopoulos from University of Chicago. He'll be followed by Avnil Gulman, University of Pittsburgh, then Vikram Singh from UCSD. And the last of our 4 speakers will be Bashima Islam from the Worcester Polytechnic Institute. And our discussants, one virtual and one on-site, will be Miriam Shinecki of USC, University of California, Southern California, and NIH's own, from the NIMH intramural program, Sylvia Lopez Guzman. So I'll invite Nico up to the stage to get us started.
Okay. While they're setting up, my name is Nico Hastopoulos. I'm a behavioral neuroscientist. And for most of my career, I've been focused on highly constrained, restrained, artificial behaviors that we had non-human primates perform. And what I want to talk to you today about is a new area, relatively new for me, looking at natural neuroscience. What I mean by that, it's a term that's been coined. It's basically looking at neurophysiological processes under more natural contexts. And I'm particularly interested in how the sensory and motor cortical areas control movement of the limbs, the arm and the hand. Most of my career, I've been working with macaque monkeys, which are relatively large monkeys. What I'm talking about today, we'll be looking at these much smaller animals, these marmosets, are really tiny, about 300 grams each. Very cute. They kind of look like Einstein with their hair, tufts of hair sticking out on the side. So what's my motivation for looking at naturalistic behavior in the context of neuroscience? Well, obviously, the brain has evolved over millions of years to allow for behavior that would lead to survival. And so obviously these behaviors are behaviors that are real behaviors that you see in the wild to help them survive. But aside from that, there's another reason. As I said, many people, including myself, looked at very simple models of how, for example, the motor cortex encodes information about behavior. And these simple models of motor cortex can work very well in these highly constrained artificial behaviors, simple tasks like the center out task, which is shown here in the bottom left. And this is a task that was pioneered by Georgopoulos in the 80s. And basically, he had monkeys trained, macaque monkeys trained to make reaching movements with a manipulandum to one of 8 peripheral targets. So there's straight line movements, and usually it's with a video screen, so it's highly artificial. These animals are typically in a chair, restrained, their heads are usually fixed, okay? And they have limited mobility. But in this context, you can look at what these cells in motor cortex encode, and here's an example of a tuning curve that's been seen now for many decades. In this context, simple context, you see the firing rate of one neuron as a function of the movement direction. And you can fit that with a cosine function quite well. And so this works great. It's a very nice, simple model of directional tuning of movement. But now if you look at something more complex, like this, in this study by Aflalo and Graziano, they monitor the movements of the monkey, macaque monkey, in their cages. And they were doing all sorts of stuff, like scratching themselves, doing whatever, grabbing for different pieces of fruit. And in this context, very simple model like directional tuning could only account for less than 10% of the variance in neural response. So we're missing something, and we're being misled, I think, by just limiting ourselves to highly constrained and artificial behaviors. So what we decided to do is work with the marmosets and look at prey capture as a model of complex motor skills. And I want to show you this video of this animal right here, if I can get it to play. Reaching out, capture an insect sitting on the branch. There he goes, he gets it, and then he eats it.
Adult male, 6 meters, cocktail of
Okay, so how do you bring this to the lab? We can't do this obviously in nature. So what we did is we have these animals in cages, relatively large compared to their size. At least you compare it to macaques, which are the workhorse in neurophysiology. And we have these cages with branches and different kind of naturalistic objects that they can engage in and engage in spontaneous behaviors like jumping, climbing, foraging, whatever, eating. But on top of these cages, we also have an apparatus which they can voluntarily choose to go up to whenever they want to. There's a little hole in the top of their cages and they like to go up, they like to be high up. So they naturally will want to explore up there. And in this apparatus, which is enlarged here, you can see we can deliver prey. These prey can be moths or crickets. And then with that, we can then record their behavior, first of all, and we record the behavior using deep lab cut, which is a deep neural network that allows us to track in a markerless fashion without physically putting markers on, which I used to do for a long time, physically gluing markers on the limbs. Here, it's all done with computer vision. We can track the positions of relevant parts of the limb and then track the motion of the limb in space. As you can see here, and we've validated this approach using kind of ground truth gold standard, which is XROM. It's called it's 3D X-ray video fluoroscopy, where we actually had markers embedded in the bone and compared it, and it did quite well. So it was quite accurate. So we resorted to that for recording the behavior. Now for the, and this is an example of one of our animals doing prey capture in the lab. Let's see if this works again. Tested it last time. Let me try it one more time. All right. Well, unfortunately, there's something wrong here. Okay. All right. There you go. There's a moth that was dropped into the apparatus. He tries multiple attempts, sometimes with both limbs. He finally gets it. The video shuts off, and then he does ultimately get it and eat it. And so from that, we can track the kinematics of the arm and these very complex behaviors. And at the same time, you'll notice on top of his head, this helmet, which is recording wirelessly the signals from individual neurons in motor cortex and somatosensory cortex. Here's the helmet, wireless transmission, recording data from up to 100 electrodes at close to 30 kilohertz. And if you look at the schematic here of the marmoset brain, you might notice if you're used to looking at brains, at least in non-human primates and humans, it's a very smooth brain. Has very few sulci or folds, and that actually is an advantage working with marmosets because we can access parts of the brain that normally would be buried in the sulcus. So relevant parts of the motor cortex and the somatosensory cortex, here M1 is motor, S1 is somatosensory, PMC is premotor. We can access all parts of that area which we normally buried in the sulcus. And these electrodes are Utah arrays, so these penetrate a millimeter into the cortex and presumably record for probably layer 5 of motor cortex, as well as somatosensory cortex. And from that, we can record from, in our best case, up to 160 neurons simultaneously. These are the average waveforms of these units that we spike sorted. And I want to also acknowledge my very talented postdoc, Jeff Walker, who really spearheaded this whole project. This is a project I've been doing together with my colleague, Dr. Jason McLean at the University of Chicago. So now we have both neural activity, spike trains from 160 neurons, as well as behavior. So my graduate student, Dalton Moore, has started to look at some of this data and to try to develop a more sophisticated encoding model, something going beyond the simple directional tuning model I described at the beginning. So he began by incorporating a trajectory-based encoding model, which is something I had worked on for many years in the macaques. And so he implemented this in the marmoset. So what this model does is instead of saying, okay, the neuron cares about a certain movement, direction, or velocity, it cares about a whole temporally extensive trajectory. And from this model, which is basically a generalized linear model or logistic regression, we can characterize the preferred trajectories. And these are examples of preferred trajectories from individual neurons in the 2D space. So basically, when the monkey makes a movement that follows that curve in this little curves, that cell will fire with the highest probability. He then incorporated a functional network analysis, incorporating functional connectivity as an additional covariate to try to predict the response of neurons. So I'll explain that in a moment. So anyway, let's start with a trajectory encoding model. The idea is you take little snippets of movement, of behavior, and you identify time point 0, and you say, okay, at that time point, did the neuron fire or not? And then you look at behavior before it fired, that's marked in blue. That's what you might view as sort of sensory, in the sense that the movement's occurring before the neuron fires. And the red is occurring after the neuron fires. That might be viewed as more motor-like. And so we have the X, Y, and Z dot velocities of the hand. And we take these little snippets of motion, feed it into a generalized linear model, which is shown here, trying to predict the probability of a spike given the trajectory V hat. And we're going to compare that to a very simple sort of proxy for directional tuning, where we only look at velocity at one time lag. It's just this little brief period of time, 100 milliseconds after the spike occurred. which is a proxy for directional tuning. And then we use ROC analysis, and we look at the area underneath the ROC curve as a measure of goodness of fit. An AUC value, an area under the curve value of 1 would be a perfect model, 0.5 is chance. And what we found, or what Dalton found, was that among all the neurons we recorded from, each point here is a neuron, the trajectory encoding model performed better, almost in all cases, than the simple velocity encoding model, the directional tuning model. That was true for both single units and multi-units. And here's an example of one of these preferred trajectories from one neuron with an AUC of 0.7, which is pretty good. This cell will fire when the monkey makes this kind of curved trajectory from blue to red. And here's another example of a kind of a crappy neuron. Basically did not fit, the encoding model did not fit very well. I'm going to skip this part because of time, but we found that the optimal duration of these trajectories was 500 milliseconds. Okay, so now to incorporate network effects, what we did was used a form of mutual information, what is called confluent mutual information, that tries to try to determine like how much does one neuron A predict about the response of neuron D in the future. And if there's predictive power between A and predicting D in the future, we say there's a functional connection, a strong functional connection. And B might be weaker and C even weaker still. So from that, we can build a matrix of functional connections. These are directed connections between input neurons, that is sending neurons on the y-axis, and target neurons, receiving neurons on the x-axis. We broke it up between even and odd reaches, and you might see, if you look carefully, they look very similar. So there's consistency in these functional connections. That's one reason we did this, we broke it up. But there's another reason, which will become clear in 1 second. So now what we do with this network models, we not only incorporate the trajectories, B hats, but we also include the functional connections that we've measured independently of this encoding model, right? Just based on confluent information. So we incorporate these terms here. These terms have the weights alpha, which are the functional connections, alpha, which are fixed, and they're not actually fit in this GLM. The only thing that's fit are the gains, the beta naught and the beta 1, and the K, which is the per trajectory. So we now have this expanded encoding model, and what we found was if we incorporate both trajectory and network effects over the population, we significantly do better than just looking at trajectory. So in summary, if you look at the full network model, a full model including trajectory and network effects over the whole population, you do significantly better than just looking at network effects or trajectory alone. So with that, I would like to finish up and thank my lab, particularly Jeff Walker, Dalton Moore, and Paul Aperture. Thank you.
Hi, I'm Avneil Guman. I'm from the University of Pittsburgh, Department of Neurosurgery. I am not an MD, so I do not open any people's brains, but being in the neurosurgery department gives me the kind of unique and lucky experience to have access to individuals with electrodes in their brains. And I'll be talking about some of the unique things that we're doing with that, in that setup. So just as an overview, I'm going to tell you a little about the setup, then I'm going to tell you about two things that we've been doing with real world behavior, a week in the life of a human brain and a moment in the life of a human brain. So what we're doing is, as I mentioned, we have individuals with electrodes in their brains. And so these are epilepsy patients who, for the surgical treatment of epilepsy, if medications either don't work or have stopped working, the one curative treatment for epilepsy is to have the part of your brain that's causing the epilepsy to be resected. And before doing so, what they do is they implant electrodes into these individuals' brains, and then they sit in a hospital bed for a week. And so, it's wonderful that we can come in and do kind of traditional neuroscience experiments with these individuals, bring a computer in and do your typical computer experiment. But what I've been thinking a lot about over the last few years is what can we do uniquely in this population that really is a type of neuroscience that's either very difficult or more or less impossible to do otherwise. And the fact of the matter is that they're eating, they're sleeping, they're watching TV, they're talking to their friends and family. And we have 128, 200, sometimes up to 250 contacts that we can record from their brain during this true real world natural behavior. So the first thing I'm going to tell you about is something that we've been doing at the very long time scale. So at the scale of taking the entire data from the entire week long and seeing what we can do with it. So real life and physiology, things like hormone levels and things like that, they change over the course of minutes to hours. Yet almost everything that we do in neuroscience are these experiments where people are doing tasks that occur on the order of 1 second, 2 seconds, and we're recording neural data on the order of milliseconds. So we know very, very little about what the brain does at these very long time scales, and particularly in a real world environment. And this gives us a very unique opportunity to look into this. I should point out my very talented MD PhD student who defended his thesis last week. So what we're doing is we've taken 20 people with these electrodes in their brains. We basically are building all-to-all brain networks, so functional connectivity between each one of those electrodes and all the other electrodes every 5 seconds for a week. So we have on the order of 100,000 of these slices of what's happening in their brain networks. We group them into regions and then eventually into networks. Right now, I'm going to be talking about natural behavior. So we are very careful to remove both the parts of their brains that are causing their seizures, that are clinically determined to be causing their seizures, and any time in or around when they have a seizure in the hospital. And what we're able to do, and the idea here is we're essentially taking these networks and we're projecting them into kind of a neural state space. And we're just watching these networks go over this state space. And I'll tell you what these colors, don't worry about the colors right now, I'll tell you what they are in a minute, but just wanted to give you an idea of what's happening. So like this is a day's worth of data for each one of these two subjects. And so this is a day-long trajectory of what their brain's doing. The first thing that we did, and kind of natural to what we're doing here, is they're also under 24/7 video monitoring. So we annotated those videos for what they're doing in every single frame. Are they on a device? Are they talking to a friend or family? Are they manipulating an object? Are they sleeping? And we asked, can we classify what they're doing? So we train a classifier based on 1 day's worth of data and ask on a second day, can we determine what they were doing every 5 seconds based on their brain network activity? And the answer is yes, we can. And some of these things this is from one subject, but in all 9 of our subjects where we have these annotations, we're able to do so with above chance accuracy. And you can see things like when they're using a device, what gets activated is their somatomotor network and their visual network, for example. The other thing that we can do is look at physiological components. So one thing that comes for free is heart rate, because they're in the hospital, so their heart rates are monitored continuously. So we used kind of heart rate variability as at least a somewhat of a proxy for arousal. And we show that we can, based on their brain network activity, again, we train the model on multiple days, in this case, like 3 days worth of data. And then we ask on the next 3 days, do we have an above chance correlation between our predicted and the true heart rate? And so we can predict, for example, their heart rate based on their neural network behavior. We also look at things like circadian rhythms. So we create an oscillation that happens over a 24-hour cycle. And again, train the algorithm on multiple days, on like the first 3 or 4 days worth of, in this case, the first 3 days worth of data, and then look at days 4, 5, and 7, or 4, 5, 6, and 7 to show that in fact, what we've trained does continue to follow the circadian rhythms. So these networks, they capture behavior and physiology consistently over this kind of real world behavior. And just kind of opening up to connect back to some of the other things, this is a place where we would love to have some of these other sensors that we've been talking about the last few days. We'd love to get actigraphy that we can coincide with what's going on with these neural networks. Measures of cortisol and things like that, so that we can understand these kinds of physiological brain interactions. And then just going back to this figure for a minute. So what this figure is actually colored by is what the subjects were doing. So, green is for manipulating an object, pink is when they're asleep, black is where we could see no detectable behavior, that is to say they're just kind of staring into space. And so you can then see from, which makes sense based on the classification that I told you, that these kinds of state space representation can tell you what they're doing and kind of goes into these specific clusters. And then we can ask about transitions in this state space. And it turns out that neural transitions correspond very well in time with behavioral transitions, which we would hope they do. And we were able to kind of verify that just by checking when they happen in time relative to chance. We've also gone on to do things like characterize the dynamics of the neural networks and things like that. And so this is what we've been doing at a week-long time scale. But we also have the opportunity to ask what's going on at the millisecond time scale during natural behavior. So in this case, what we're actually doing, and a very good PhD student in my lab, is doing continuous eye tracking while they're having conversations with friends and family and just going about their day. So eye tracking glasses, for those of you who don't know, are essentially a mobile eye tracker where there are two cameras facing inwards towards the eyes and one outward facing camera. The outward facing camera gives you their field of view, and then the ones that are facing their eyes are the ones that are allow you to tell you where they're looking in that field of view. And so you get data like this. And just to give you a sense of what the data look like, so on the left, what you're seeing is a single frame from the eye tracking glasses that have been annotated by computer vision algorithms for the objects and faces in the room. And then the orange cross is where they're actually looking. And on the right-hand side is the neural activity that's being recorded simultaneously with that frame being captured. And I think it's always helpful to kind of see what it all looks like together. And I'm having the same problem with, there we go. There we go. So just to give you a sense, it looks like what you would think. The person's looking at individual number one, which happened to be the patient's best friend, and the man's her husband. So she looks back and forth while they're talking. The people are gesturing, they're talking, and then goes and looks at their cell phone, and you can see the neural activity flying by at the same time. So true real-world natural recordings. And so what we're doing is what we've concentrated on is all fixations to faces, in part to kind of better understand, in part because I have an intrinsic interest in social and affective perception, and because from the perspective that kind of narrows down the kind of visual information that we have to capture and we have to model. I'm only very briefly going to talk to you a little bit about what the actual computational model looks like. And really all I want you to know is what we're doing is we're creating what's called a latent space that sits between the neural activity and what's being perceived. And that latent space is defined by maximizing the correlation between the two. And then what we're able to do is again, do something like train the model with an hour worth of these data, and then look at the next half an hour or 15 minutes and ask, can we do things like reconstruct which faces that people are looking at? And for that matter, can we understand the neural activity that correspond to these faces? So what you're seeing right here is on the left is the face that someone was seeing on a single fixation. That actually happens to be my ex-lab manager. In the middle column, what that is a computer vision model that creates about a 225 dimension that essentially parameterize that face into about 225 dimensions. And then you can visualize that parameterization. So that middle one is just a computer vision model of the first one. You'll see it loses the glasses because the computer vision model does not have glasses. Then the last one is the crazy one. That is a reconstruction of what we believe, of what the model believes the person is seeing based on the neural activity alone. Now, to be clear, we're reconstructing the computer vision model, not the original image. So we're reconstructing that 225 odd dimensional space. And a very, very much hot off the presses. Now, of course, at every fixation, the face is moving. And literally, I got this slide, the first version of this slide 2 days ago, but the final version of the slide this morning. Let's see. Our reconstruction are moving. So we're not just reconstructing the face that they're seeing, but we're actually reconstructing the motion of that face that the person's perceiving based on the neural activity alone. And then just so you get a sense that this is not just one individual, we get multiple different identities, expressions, head poses. We're modeling all of those things in this 225 dimensional space for every face that they're seeing. Now, of course, to do neuroscience, what we want to do is the other way. We also want to do the other way around. So this is modeling, this is taking the neural activity and making a reconstruction of what they're seeing. What we can also do is then take that middle column, the computer vision model of what they're seeing, project it through the model and make a prediction of the pattern of brain activity that the person was having in response to that, and compare it to the actual brain activity. So what you're seeing here now is not a comparison between the true and predicted, but is actually the correlation, the R value between the true and predicted across all the fixations. So what you can see is there's places we get up into the 0.4, 0.5 correlation range between the predicted neural activity and the true neural activity. The other thing just to point out from a neuroscientific perspective, this is the part of the brain that's been recently kind of characterized by Leslie Ungerleider and David Pitcher as almost a third visual stream for understanding social interactions and social perception and things like face motion and things like that. So, and interestingly, across the 4 or 5 subjects that we've done, this area consistently lights up in every single case as being very important, essentially, to our reconstructions of the face. The other neat thing about this model is because of this latent space, what we can do is we can move around this space. And so what we can ask, for example, is if we move in one dimension of this space, what's going to happen is both the brain activity is going to change and the face is going to change, which gives you a sense of what features of the face correspond with what aspect of the brain activity. So for example, in this dimension, it's one that, let's see if we can get that to play again. It was one that really kind of showed identity because you can see this face changing from one identity to another. And then you can see the brain activity as how it corresponds to that change in the face. And similarly, here's another dimension that's really much more about head pose. So you can see as the head pose changes, this is how the neural activity changes. So this allows you to kind of find scaled hypothesis, both generation and kind of data-driven hypothesis generation, and then testing as well, because we can manipulate changing the face in a particular way and ask what changes in the brain. And that's what I got. I wanted to thank the one people I can absolutely not forget to thank are the patients who allow us to do this work with them. They're incredible, and it's an incredible opportunity to do so. So really lucky we get to work with them. And Vikram, I believe, is coming up next.
Hi, my name is Vikram. I'm a neuroscientist at UCSD. And Nico has already done the heavy lifting for me for marmosets. But so the perspective I would like to give here is why we need to make sensors. Why do we even need to make new sensors and new technology? And are they just helping you get better data or more data, or they really change your perspective on like what you see? And in science, it's much more important because when you keep generating data over and over again in a certain fashion, they lead to certain assumptions in the field. And then those assumptions dictate everything else which is designed afterwards, every experiment that is designed afterwards. So if you are limited by what you're collecting and what you're looking at, then you'll always be pigeonholed into it and probably not represent reality. Now, I'm going to talk about vision because you're going to start somewhere. So we start looking at vision. And so we know that vision evolved a long, long time ago, but we also know that vision actually evolved for a very specific purpose. Okay, so like for every animal, the vision is tailored to how they live and how they see the world and what they need to do and what they request from the vision. So vision actually is more of an active process than a passive process where something falls on the retina and brain does something. But actually it is the other way around. It's the animal who wants something, so the vision has to be a certain way. And this is another video of an animal, which Nico also showed, is trying to hunt, but also if you pay attention to how the animal is moving, if the animal makes a wrong move, the animal will fall, and instead of getting food, will become food, right? So the stakes are really high, but at the same time has to use vision. So when we talk about in neuroscience that we are doing brain computation and we're trying to learn how brain really computes, we always study it in such isolation that we are really not appreciating what brain is actually capable of doing, which is do everything at once, and it has to be compartmentalized, but you have to do everything right. So how do you study vision? But studying vision is not really easy because you need precise eye tracking. And for a freely moving animal, having precise eye tracking is actually really, really hard. And that is one of the reasons why it has not been done. So that was the objective when I joined Corey Miller's lab. So the way we went for is our animal model is the common marmosets. It's a small monkey, roughly the size of a rat, roughly the weight of a rat. And we're going to use the advancement in technology, sensor technologies, with 3D printing and wireless recording, which Nico also showed. So in terms of making the device, these were main consideration that I had. One is it has to be lightweight because these are small monkeys. They cannot carry a lot of weight, but you roughly know what kind of weight they can carry because they carry their babies on their back. And at times they are able to carry 2 babies. So they can roughly carry about 70 grams or so for a short period of time. I don't think they can carry it for like a very long time. And then it has to be power efficient, and you have to have camera synchronization and pupil tracking. So the way we go about that is there are 2 parts. The whole system has been split into 2 modular parts. One is actually the head assembly, which has 2 cameras. One looks forward like a GoPro, and the other one looks at the eye. And the second is what they wear on their backpack, which is the brains of the whole system, and it has the microcontroller that I was showing before. So in the section D, you see is our monkey Mo, who's wearing all of this at once, and it's just chilling in the arena. Now, why is it even important, or is it just like we are forcefully doing it, and it's, we are doing it because we can? But like, here's something which will be a motivation for this, is this is a little bit of a audience participation. So you're gonna look at the eye, and this is a video, so the video is gonna move. Now, since it's a head-mounted eye tracker, it's hard to tell if the animal is moving or it's sitting in a chair. Now, you have to raise your hand if you think the animal is freely moving, okay? I hope I can play this. Okay, how many people think actually that the animal is moving at this point? Okay, some people think that it's moving. How many people think the animal is moving now? Right. So what this is actually about 10 seconds, and about 5 seconds, the animal was sitting in a chair, and the other 5 seconds, the animal has been removed. So the eye tracking is pretty stable. So it's very hard. Just if you keep looking at the eye, it's very hard that the animal is moving or not. But if you look at the behavior of the eye, it changes so drastically. Although if you look at the vision neuroscience, you will see most of the data which is collected is the first 5 seconds, the way it has been collected, it's completely dissociated from all the other and natural behavior the animal will do in a naturalistic setting. So now this is the overall setting. What we have is an arena. The animal freely moves around. There are some dots in there. They have a different purpose, and probably I'll touch on it towards the end. And we have 2 cameras. One is the world camera, which shows us what's in front of the animal, and the eye camera, which shows us where the position of the eye is. And so the first question we wanted to really address is it even usable? So what we quantified is like, this is like first pass, is like how much the animal moves wearing that system versus not wearing that system. And we are able to see that significantly, it doesn't affect anything significantly. And the animal moves more or less the same speed, more or less same time, and more or less the same speed across the session. And all of these sessions are about 30 minutes long, and some of them are like 1 hour long. We don't keep the animal out of their cage more than an hour. And this is the occupancy map. It kind of changes. but like this is just to show that if they wear it, they go all around the arena instead of sitting at one place. I'm gonna skip this one. Okay, now the other big problem is that you had designed a system which can record the eyes, but can you do eye tracking? And in order to do eye tracking, you should be able to actually find where the pupil is and really find the center of it, and then from there you figure out where the animal is trying to look. But this is actually hard in the system that we are doing, because our illumination is actually not fully controlled. When the animal is sitting in a chair, you can control the illumination, the angle of it, and then you can just apply a simple threshold, and you can find the darkest spot, which will probably be the pupil, and then you can find the center of it. But in this system, when the image is something like what you see in A, it is really hard to do that. So one thing you can do is you can actually train a neural network to actually find the pupil for you and do the heavy lifting for you. So what we are using is a segmentation neural network. So most of the neural networks that we talk about are mostly classifiers. They will tell you if this is a cat, this is a dog, and they will also tell you with what confidence they think it's a cat or a dog. But this is a segmentation neural network, where what it does is instead of classifying a whole image, it classifies each and every pixel. And it tells you with some confidence if it thinks that pixel is part of whatever it has been trained on. So is this pixel a part of a dog, or is this pixel a part of a cat? And that way, what it does is it actually generates an image back for you. Wherever it's white is where it thinks that feature exists, and wherever it is black, the feature doesn't exist. And that is the approach we took for the eye tracking. Well, it's very easy to train. Takes only 10 sessions. I can do it on my laptop. So that was good to know. And this is an example of if I use the old school thresholding approach, then I will fail. I have a lot of like artifacts. While if I take the unit approach, here, I get a much better result, even with a very poor quality of the image. And this is in comparison with like the state-of-the-art eye tracking, which is Harrington system, with our system, which we call Cerebro. And they are comparable. I'm able, at least in chair, there's no way I can compare them when the animal is freely moving because the other system is very heavy. But in the chair, they seem very comparable to each other. This is a strategy to find where the animal is looking. You're recording from the eye, but you really know where the animal is looking, so you have to calibrate. But what position of the eye means how many degrees from the center. So the way we do it is we show them marmoset faces on a screen, and they make saccades to it. And recently we have been doing something called as a smooth pursuit, where you show a moving target, and very naturally, they are inclined towards like looking at a moving target, and you can get all the calibration in just like 2 seconds of the animal's movement. Okay, so now in the next figure, this is all put together, whatever we talk about. So let me just go over all of them, and then I'll play the video for you. So this is our monkey Suki. She's in an arena. This is the eye camera. This is the world camera. This is the result from the neural network which we are getting. This is what we are using OptiTrack to track her head and see how far she is from the target that she's looking at. So there's a gaze projection on that. This is the heading, which means which way she is like oriented in the arena. This is the position of the animal, so actual position of the animal. And this is the neural activity from a primary visual area called V1. And one thing which I want people to note in this is like there is a behavior which is not rat-like at all. If a rat will be left in, or a mouse will be left in an arena, the way they will sample the arena is they will quickly run around and they will sample it to make a sense of where they are in the world. But a primate can do it with like no problem. What they do is they sit in the center. That's what you might have realized is like Suki doesn't really move. He finds a sweet spot and within 10 seconds has spanned the whole arena and has the complete map of the area. So that is like something very primate specific. And that is something, if you are studying vision, primate vision will act very differently than what you will expect from an animal which is not designed for that or has not evolved for that. Well, so what we were able to find is if you look at the video, you will see like the world camera video is like, it's crazy. Like the speed at which it moves, it seems like the animal should not be able to see anything. It's like everything is changing so fast. And that is true even if you put like a GoPro on your head and go biking. If you play back that video, it will look insane to you. It's like, it will be like very shaky, very, very difficult to see. But when you look at, but in your actual experience, it has been always very smooth. So the way biology has solved this problem is you can actually subtract the head and the eye movement. So what happens is your head moves in a certain direction, your eyes actually compensate for that. So that way you are able to maintain your gaze at a fixed position. So that's what we are able to see is that the head moves and the eye moves in this like bursts. And then it goes in the negative direction of where the head is going. And if you sum them up, you can get what is the gaze. And that gaze is actually just flat. So the animal is very stable. Animal's view is very stable, although the head is moving a lot and the eye is moving quite a lot. And in interest of time, I think you can skip it. And the only thing I would like to talk towards the end is, well, after developing this technology, what we are able to do is fundamental neuroscience with it. So right now, what we have is, this is the neural activity of the animal when the animal is head restrained and head free in the same session. And these are certain tuning curves that we talked about earlier, is we can listen to certain neurons which have a preference for a certain orientation of the grading or a spatial distribution of the grading. And you can find that, which is very fundamental vision neuroscience using our system. And what you can get is also called a receptive field, where there is a neuron which particularly likes if something is at 5 degrees. And then these are stack of neurons. Somebody likes 5 degrees, somebody likes 5.5 degree, and so on and so forth. So you can actually get receptive fields from this. And well, yeah, that's about it, actually. I'm going to skip the future direction. And I will thank Miller Lab and especially Jingwen, who helped me run the experiments, and Brain Initiative fundings, which made all of this possible. Thank you. So the next speaker would be Dr. Basma Islam.
Hello, everyone. First of all, thank you so much for giving me the opportunity to be here and present my work to you. My name is Basma. I'm from Worcester Polytechnic Institute. And today I'm going to talk about my work on understanding behavioral development using multimodal ubiquitous systems. So let's start with, what do we mean by behavioral development? So behavioral development is a behavior analytic approach that allows us to look at the behavior changes of both basic skills and complex skills across the lifespan of a human. So when we talk about basic skills, it includes the motor, the language, and the cognitive development of babies when they grow up. The complex behavior involves concentration, sensory clarity, and equanimity, which can often referred to as mindfulness in one word. Now, the major question that we want to ask is how we can monitor a cognitive development or a mindfulness skill development in a human. One solution can be we can look into EEG signals, which can give us the brain activities. However, the EEG signals are not very good or very useful, I would say very easy to access in daily life because there's only timed recording we can do. They're often expensive and they constrain the user who is using it. So we want to ask the question that can we use the wearables that we use in our daily life or the wearables that are easier to use to do passive longitudinal monitoring in the wild? So that does not affect the way the person is behaving. And we found that the answer is yes, but only wearable itself is not sufficient because to understand the complex behavior or the basic skill development, we need to have multiple of these wearables in the person, which is often constraining, and they also need to be time synchronized with each other, and they also can have faulty sensors. So we try to understand if artificial intelligence or deep learning and these techniques can help us in getting this mindfulness or this cognitive or other behavior development information from the wearable devices. So along with my collaboration, my team is looking into two specific topics that look into behavioral development. The first thing we're looking into is child development delay monitoring. And the second topic we're looking into is mindfulness monitoring. For the child development delay monitoring, me along with my collaborators at UIUC have developed a platform called Little Waves. It's a 1 ounce lightweight platform that has a motion sensor, an ECG sensor, and a microphone or an audio sensor to record. This small device sits in a pocket of a shirt on the chest of the baby. And so far, we have collected data from 210 children who are between 2 to 24 months old. And we have collected two types of sessions of data collection. The first type of session includes 30 minutes of virtual visit, where we have the video ground truth data of what is happening, what the baby is doing. Then we have a 2-day-long home visit, where we do not have the video to preserve the privacy of everyone around the baby in the home. But that data is significant because that also allows the parents, the caregiver, the sibling not to behave different when we're collecting the data. Our goal is to use this multimodal data to understand the action the babies take, the interaction with the parents, the sibling, the caregiver, and understand the environment around them. So due to the shortage of time, let me quickly talk about the action. So when we say actions, we mean multiple things. So we mean position and body movement, which gives us the motor development of a baby. We include vocalization, which gives us the language development. And we look at sleep or consciousness state, which gives us the cognitive development. So when we're working on position estimation, the first challenge we found that we are having a single sensor replacement. So we have one device that has multiple sensors, but the device is on the chest of the baby. And it allows us to lose many spatial information which we would have if we had sensors connected at different limbs, for example, in our hand, in the baby's hand, and the feet. So we lose the spatial information. And we can see that that's why our kappa is like 0.41. The second problem we found that, and it was discussed also yesterday too, that the movement by child and adults are not the same. Because if you look at a baby, their limbs are much more shorter, so they have much more noise propagating to them. The second problem is that any action taken by babies are not as smooth as adults. They're more jittery. They have more noise in it. And you can see the effect because when we use models that are developed for adult position estimation, like Limobird or adult activity estimation, they do not perform well when we put babies' data and we want to see the performance. However, we observed that we can go to kappa of 0.69 for babies if we can learn from the 2-day-long unlabeled data where we do not know what the baby is doing at that time, but we have the data. So here I'm showing an overview of a proposed model where we have, we take the 3-channel accelerometer and gyroscope data, so we have 6 channel of data, 6 degree of freedom data, and pass it through this unsupervised machine learning model whose idea is to understand what are the correlation and what are the effect, what is the context that's happening with the IMU. And from that, with only those small 30-minute virtual visits where we have the ground truth data, we can extract useful information like the position of the baby. We can do similar approaches for electrocardiogram or ECG data to understand the restfulness or the exertion states of the baby, which together can tell us important information like if the baby is in tummy time. Then, when we want to look into the sleep of an infant and understand if the baby is sleeping or not, we see the same trend. Because it's only on the chest, the IMU does not give us all the sleeping states, because if the baby is moving their hands or feet, not moving their whole body, it can be presumed as, okay, the baby is probably sleeping, but they might not be. Similarly, the audio data, if it's calm and quiet, that does not mean that the baby is sleeping. It can be the movement, the baby can be awake. But we found that using the three modalities, the audio, ECG, and IMU, we can increase the accuracy of identifying the baby is sleeping or not sleeping by 7 to 10%. So along with this works, we're also looking into understanding the environment, like if there's household chaos, can we detect the household chaos which affects the development of the babies? So now, let me quickly switch gears and talk a little bit about what we do in mindfulness monitoring. So for mindfulness monitoring, we are focusing on mindfulness meditation, which allows us to do an open and receptive point of view for the present moment. And research shows that mindfulness training couples resting brain with dorsolateral prefrontal cortex. But it's not often possible to look at people's cortex to understand if they're in a mindful state or not. And that is an important question to ask, because we have found that many meditators, specifically the new one, did not know if they're doing things correctly or wrong, what they're doing is right or wrong, and they do not perceive to continue this practice. So our hope comes in from the literature that shows that even without continuous regulation in breathing, mindfulness meditation changes the respiratory signal in a unique way. So we can ask this question that, can we monitor our breathing and have respiratory signs estimate our mindfulness growth? And to do that, we want to use the everyday objects used by the user. For example, the smartphones or the AirPods we use, we often forget are in our ears. And the reason to do that, we don't want to constrain the user by asking them to wear a chest band or a vest, which are pretty expensive, like Hexos can cost $500. So in general, the question we're asking is, can we hear our breathing information? And to answer that, we did a study with 131 subjects of healthy and respiratory patients. The first thing we observed that it's not possible to get this complex information only with signal processing. So we moved towards deep learning, which can give us most complex information and can extract more complex features. But most deep learning algorithms need annotation. So our goal here is to look at the inhalation and exhalation phases. And while annotating, we found that there are borders of these phases where inhalation ends and exhalation started, or exhalation ends and inhalation started. Those are inaudible to human ears. So it's very hard for annotators to annotate that phases. They can say how many heart rate was there, but not, or how many breathing rates were there, but not where the phase ends and where the phase starts. This can be done with some of the IMU data, but you have to hold the IMU on your chest or somewhere, and also it's a lot of data to annotate. So even though machine learning and signal processing cannot work alone very well in this scenario, they can work very well together. So what we want to do is we use the signal processing with IMU data only on training and transfer that knowledge for deep learning-based audio data. We're calling them teacher student, and learn only from the audio data to go ahead in the training, on the testing demo on the real life. And this teacher student model are traditionally trained with two deep learning models. So the main contribution we were having in redesigning it to have a teacher model, which is signal processing based model, does not require annotation, and using that to guide and lead the deep learning model of audio to understand the inhalation and exhalation phases. And we found that we can identify inhalation and exhalation phases with more than 77% accuracy. This leads us to use and finally ask our question that how much the respiration signals have effect and how much we can get the mindfulness skills out of them. And what we observed that we can understand how much, if there's a mindfulness would happen or did not happen, with 67 to 82% F1 score using the respiration signals. But in the future, we want to understand how much that is. But for now, this result shows if increase or does not increase. So before I end my talk, I very shortly want to talk about the other thread of work I do, which focuses on-device deep learning on battleless platforms. So the idea is we want to understand from the semantic diversity of the data and the context, how much processing do we need? So we can do much more complex computation in tiny devices. And this will allow us to move forward to my future goal to perform these developed AI models for behavior monitoring on these tiny batteryless devices, which will allow us to move forward to provide a more cognitive and more holistic solutions. So before I end, I want to thank my collaborators for supporting me and these young researchers who have working very hard to make this happen. And thank you so much for the time.
We'll wait for our speakers to come back up, and we have Miriam Shineki to join us online. Laura, yes. Yeah. Laura's and Laura. Hi, Miriam. I think you want to test yourself? Great. So just to get us started, we'll start with our discussants, Miriam Shineki and Sylvia Lopez-Guzman, and as well as Laura, our three discussants, to sort of ask our speakers, give them their reaction, and ask our speakers a question that came to mind while they were giving their talk. So why don't we start with Miriam?
Okay, great. Hi, everyone. Sorry, I couldn't be there in person. I actually had a question first for Nico. So as I was listening to your talk, I agree with you. It's really important for us to go towards more naturalistic behaviors and monitoring. But as you know, when we go towards these naturalistic tasks, accounting for internal states and their changes over time could be quite important. Context changes and how those may change the neural representations of, say, movements or reach and grasp. How do you think we should account for internal states in these kind of scenarios? How do we monitor them, and then how do we take them into account in our modeling? What are your thoughts on that?
Okay. Yeah. Yeah, that's a good question. Yeah, more sensors, I suppose, is the short answer. More sensors basically is the answer. But as far as one of the things that we stress is that we're looking at various behavioral contexts, natural contexts, and we feel that by freeing up the animal, at least we don't have to worry about adding stress to the animal, which I think affects the responses we're getting. So like with traditional approaches with head fixed, constrained macaques, very often even fluid restricted, these are not natural conditions and they induce a lot of stress on the animal. So we're learning something about a stressed animal, whereas in our case, these are not completely free to do whatever they want to do. By the way, we were talking last night about informed consent. Now, of course, these animals don't have informed consent in terms of what we put in their brains, but they choose whenever they want to go up to the apparatus and do what they want to do. It's totally up to them. They're completely free. We don't constrain them in any way. So at least we don't have to worry about the issue of stress affecting the responses.
I see. Interesting.
And maybe why don't we get Avniel's take also on that from a different species perspective? Not that you're a different species, Avniel.
Thank you. Sure. For me, the thing that I think about is, I gave you our two different perspectives, a very long time scale and a very short time scale. And ultimately, I want to bridge between the two. And I think that will start to get at some of these answers, is how do these things that we're learning at these very long time scales that are changing over minutes to hours influence what's going on a millisecond to millisecond basis. We're not there yet. It's early days, but I think that's how I see what I'd like to see, some of this work that I described going, is as we start doing more and more rich things at these different time scales, also thinking about how they come together. And I think that ultimately gives you kind of a neurocognitive context for what's happening on the millisecond level.
Yeah, and it may be that some unsupervised kind of machine learning methods that try to also extract latent states that correspond to internal states, and as well as latent states that relate to behavior at the same time could help address some of these problems, even in the absence of explicit measurements, because as we know, internal states are very difficult to measure anyways. So maybe that could also be helpful.
Thanks. Now we'll go to Sylvia to ask a question or get reactions.
Yes, thank you. My next question is for Dr. Islam, but I think it could also apply to the other speakers. So to the degree that the models that we develop are constrained by the data that we collect, right? One question that I have is external validity. So in the data that you presented, Dr. Islam, you showed that you have pretty good accuracy at utilizing your sensor based data to predict whether the baby is asleep or is lying down or there's chaos in the house or but the question is then actually to what degree these become predictors of the, I think, like things that we care about clinically, things like, for example, developmental delays. And the same applies to some degree to the questions that were just answered about natural versus naturalistic environments, right? There's always, I think we are moving in the right direction, both in the animal research and in human research, trying to capture more of the real world behaviors, but we're also very constrained by the artificialness of collecting these data. So can you comment on that?
Thank you so much for the question. And that's a great question. I think the machine learning models can only learn what is about what the data has been fed. It's very hard for these models to learn something it has never seen. There are works in this domain to look at few-shot learning or zero-shot learning, where you get some data and almost no data, but use other contextual information to learn about what you have not seen before. And what I have found that in this type of work, where we look into the cases where we need natural data, it is more important to get data that are not inside the lab scenarios, that's outside at home. For example, one of the things we are doing is, even though we are having a lot of unlabeled data, the main reason for getting such unlabeled data is these are having at home. We send the little bit device, we courier it to the parents, they go or hop on a Zoom call with us to set it up, and then we do not see what happens next. So that allows us to collect a lot of data which are unlabeled, because if we say, oh, we are going to video everything you're doing for 2 days, or let's say 16 hours, there can two things that can happen. One, they won't agree to do that. Second, they might agree, but be very staged behavior for those 16 hours. So by losing the ground truth, we are making our lives harder, but it does allow us to have access to a group of data that does not have that much effect of being monitored or an artificial effect. And I think for the machine learning perspective, looking more into personalization, the few-shot learning and the zero-shot learning approaches, where we can look into, where we can train the machine learning models or lure the machine learning models to understand things it has not seen before by giving different contexts. For example, there has been work on audio-based few-shot learning, which looks into the textual domain to understand sounds it has not heard before. And I think that's a direction we could move forward in this behavioral development domain.
Thank you very much. Laura, do you want to jump in?
Yeah, so my question is particular for Dr. Graham in terms of human behavior and the EEG for epilepsy. So most of the conference we've been hearing about these sensors that are more like external, right? But when you start to get more, I'm gonna say invasive, like physically invasive, right? You get more, different type of data, which, we want that type of data as well. But then I'm thinking, what would be like the type of ethical challenges that you see in bringing these two worlds together, right? Data from more invasive type of technologies with data that we are able to just record from more like day-to-day type of sensors.
So, I mean, I'm going to take a little bit of a twist on the question, if you don't mind. The one thing that I think about a lot when we're talking about this natural data is we're also, we were talking about standards and data sharing, and we live in a world of data sharing. And so from our perspective, the invasiveness obviously gives us a really nice resolution into the brains, but it does the kind of generalizability. And one of the things I have been also wondering is to what extent can we do similar things with scalp EEG, which would eventually start to bring it into connecting it with some of these other things. But the thing I also think a lot about is how do we share these data, given that we have videos, we have all this very personally identifiable and personal information. And I mean, I know that's ubiquitous across a lot of the kind of human work that we're talking about, particularly in the homes and things like that. And so, I mean, I've thought a little bit about I'm involved in a consortium on what's known as federated learning, where you essentially train your algorithms on data that someone else holds. And you never actually get the data, but you get the trained model back. And so from that perspective, there may be ways to think about data sharing that can bridge across, relevant, not just to the kinds of things I do, but to all the different kinds of natural behavioral data that we've been talking about over the last couple of days that may allow us to kind of protect all the confidentiality and, from those kinds of ethical issues. I also think about, and so I think that we need to start thinking about kind of new infrastructures for how we're going to start sharing these data. And then I also have, I work with a bioethicist where we also worry about ongoing, consent. So we have this concept of ongoing consent, where we consent people not only at the beginning, but at the end of every session so that they know what what was just recorded. They get a chance to kind of vote up or down whether we get to use those data. So I mean, I'm very concerned about the bioethical concerns, and I think I got to some aspect of how it connects to the other things. But yeah.
Thanks. I think, go ahead, Nico.
Yeah, I mean, I'm not sure if this addresses your question, but I guess you were concerned about the invasiveness of these technologies. Was some of your concern? So with regard to that, I have very strong opinions about this. Unfortunately, as it stands right now, the technology is not there to do the kinds of work we really want to do to understand the brain at the right level, to do it non-invasively. And in particularly in the context of kind of the work that we do with brain-computer interfaces, brain-machine interfaces, there's just no systems out there that are non-invasive that give you the kinds of resolution that you need to provide the kind of not treatment, but allow people to really interact with the world in a useful way. It isn't there yet. Once it's there, I'll be happy to use it, but it's just not there.
Thanks. We may come back to that in the more closing discussion. Also, before we move on, I wanted to take a moment because I did forget to introduce Laura at the very beginning of the session. This is Laura Cabrera. She's an ethicist at Penn State, and I wanted to make sure that you were introduced since you've already contributed so significantly. Why don't we start with questions that are coming online, at least one, and then we'll go back and forth.
So there's a question from the audience that echoes a prior question that was raised. This is directed to all the panelists. How do we possibly expand this current technology or technologies to estimate internal states such as emotions in a realistic setting? For example, as in monitoring depressive symptoms in patients with depression.
So why don't we start with Ephraim, and I'm going to also relate that to a previous question, and that is, how do we take all this data we're collecting and relate it mechanistically to an internal state or an internal process that we're interested in? And maybe Ephraim, why don't you start?
Okay, so my straight answer to that would be, well, it's complicated because you have a multidimensional data, and that's why it has to be. Okay, so it is multidimensional, and that's why people keep going back to neural networks because they are so good at abstracting. And once you start abstracting and you start finding these clusters, and then you know that this cluster usually co-aligns with this emotional state versus the other emotional state. So there isn't some way you can actually get very close to the state which you're trying to study. Let's say you want to figure out if the animal is depressed or the human is depressed or something like that, and maybe some activity you have recorded and it clusters there. But the problem is, it is something on which you have already annotated that was depression or that was something like that. But if you find a cluster which is in between, there is no efficient way for you to say that if there is a cluster between, let's say this was depressed and this was not depressed, but you find a cluster in between from a neural network, it is impossible for you to say that is this person half depressed or half like it can actually mean completely different thing. It's a very different dimension. So like what I would say is like you can, if you have been measuring behavior and you can validate it with behavior, yes, you have a way for sure. Otherwise, if you are using just the output of a neural network to interpret what is going on, then I would say that's a slippery slope. Like that's not. Did I answer that?
I see Sylvia wants to jump in and after Sylvia, Miriam.
I think this touches on a very interesting topic, which I think applies to all the presentations today, which is the issue of interpretability versus prediction, right? So training our models to predict, whatever thing we're interested in, it's looking at this particular thing, or it's interacting with the phone, or is very different than understanding the mechanism, right? And interpreting then the, how those computational models are behaving and whether that actually tells us anything perhaps about the brain. So can you comment a little bit on that trade-off between predictability and understanding?
Hey, were you unmuting because you wanted to jump in? No, I guess. Okay. Why don't we take another question? Jonathan, why don't you go first?
Thanks to all the speakers. I just had a general question about what happens during learning. So this is sort of gets to Avniel's question about looking at integrating the time frame of short-term and long-term. Itzhak Fried has some nice studies showing that recognition of faces and face cells in hippocampus develops for the doctors and the nurses in the neurosurgery suite over time as the patient's being recorded. So it'd be interesting to know from a behavioral standpoint and also from a neural standpoint what the representation is. And the same thing could be true for Nico, like looking at what happens when you train an animal on a task and then see freely moving, how that changes the way not only the behavior unfolds, but also the neural representation in terms of the trajectory. So, I'm just curious whether or not, and also it's true for breathing, like, whether you develop better breathing techniques, how does that evolve over time? And how does that manifest it in terms of this connection between the neural and behavioral? So I wonder if you guys could comment on the opportunities here for studying over a time course, these interactions in a learning setting.
I can speak to that. We're actually beginning to do work on learning, on motor skill learning. This is experiments that are slightly less natural. So instead of prey capture, we're actually training these marmosets to interact with an iPad to grab little beetles that are moving around in space, and so they're learning a skill. It's comparable to a serial reaction time task. And we're looking at that over extended periods of time, over a week, maybe 2 weeks, and also looking at the role of sleep in consolidating these memories. Because we can record wirelessly, we can record it in sleep as well as during the day. I guess one of the challenges we have is if we're going to stick to the single unit level, is it important for us to track the same neurons over those 1 or 2 weeks? And that's a bit of a challenge. We know we can't track every single neuron, the exact same neuron over a 2-week period. Not all of them. Some of them we can, but that's a challenge.
I also want to jump in and say something that when we are developing skills like meditation and like mindfulness meditations, over sessions, the skill set of the person evolves. So the person who has done the first session in meditation their changing or their behavior will evolve when they're doing the 10th session, because now they know more what they want to do. The first session, they're like, okay, do I do this or that? Should I breathe in or breathe out? What should I do? Is I look sound here or look at there? So the trainings over time, they develop and they changes the signature. So this is one of the other things we are trying to look into, that how much the correlation is, or how much is the change happen if we clustered in two different groups, where one group are expert meditators who have done it before, like at least for 5-6 months, and people who have not meditated more than twice in their life. So what are the relation between them and how much it changes the respiratory signature?
Going to have to stop there. So I'm going to ask us all to thank our speakers and discussants for session 5. So we have a 5-minute break, and then we'll move to our closing discussion. So as you all are happily discussing, why don't we wander back to our seats, except those who should be coming up here for the closing discussion. So we have Jeff, we have Kirk Brown online, right? No, on stage, sorry, Kirk. You have Jeffrey Cohn. We have Ashe and Catherine virtually. And we'd like to have Laura come back up. So I think that covers everyone. That was just a school teacher's call to get everybody on stage. That was not their formal introduction. I am here, though, to formally introduce Lizzie Enkadowicz, my colleague in the Brain Initiative, whose home institute is NIMH. Lizzie has wears many hats. She is the program chief. She's the director of the multimodal neurotherapeutics program at National Institutes of Mental Health. And the overarching goal of the program she runs is to advance neurotherapeutics for major mental disorders and clinical dimensions of psychopathology through a non-siloed, personalized medicine approach with an emphasis on synergistic effects of combined and multimodal approaches. And those are approaches to actually monitor behavior and track neural activity. As consistent with that, she's an integral part of the brain behavioral quantification and synchronization team, and part of the Brain Initiative's brain research through advancing innovative neurotechnologies. Oh, that's us. That's the Brain Initiative. Sorry. So she's part of Brain and she's part of BBQS. Again, you'll learn more about her as she runs this last closing session, where we hope to give you a synthesis of what went on and some overarching, some high-level reactions. Lizzie?
Thanks, Holly. And just thanks to everyone here for joining us for our final moderated session. The goal of this session, as Holly kind of alluded to, is to provide an opportunity for discussants to integrate and synthesize the wonderful information that we have learned about, from biophysiological sensors to environmental sensors in the past couple of days, and to think about how to apply these sensors across novel contexts, and also to consider future directions for ways in which we can advance research using sensors to help us to understand how the brain gives rise to behavior. So just so I'm clear with the discussants, that we're going to start off with kind of a round table type discussion with both online and in-person panelists. So we've already kind of rallied the group here, but I just want to introduce Dr. Kirk Brown from Carnegie Mellon, Dr. Jeffrey Cohn in person from University of Pittsburgh. Online, we have Dr. Aisha Gunduz from University of Florida and Dr. Catherine Scangos from University of California, San Francisco. We'll also ask the chairs, the co-chairs, John and JC, to join us on stage for the discussion. And I think if we can, I'd like to start off with some observations from our online discussants. Catherine, would you want to start us off with a couple of questions or comments about kind of your what you've been thinking about basically for the past couple of days as we've kind of seen these wonderful talks.
Sure. So first of all, it's great to be here. This has been a fantastic 2 days. I think the presentations have been just tremendous and very insightful into where we are looking currently and where we can go together as a community. So over the past 2 days, I kind of have seen 5, I would say, main advances, but also challenges where additional research is needed. And the first of those is in sort of biosensor development. And we talked a lot about this yesterday, but also some today. And so this is making devices smaller so they can fit into cells, having adequate power. So low power devices that harvest energy from actual human bodies, right? And alternatives to Bluetooth so that we can be battery free. And then, together with that are the advances in flexible electronics so we can have this intimate integration with the human body. So, that we've talked yesterday about the silicone sensors, the bendable electronics, the skin interfaced, wearable sensors, and the ability to have some of these types of devices already in the ICU, monitoring babies, helping to develop skin for robots, through body net, these networked wireless flexible body sensors, and then having sensors that can access more deeper into the body non-invasively. And this came up in the discussion today, but also yesterday, and some of the discussions with the electronic skin and being able to measure cortisol and serotonin, drug levels through sweat. And actually even generate the sweat. And then other newer technologies, such as using bioimpedance or radar. So that's one of the areas that I saw as a major need for development, but just such exciting advances. The second is really how to manage this dynamic environments, right? We have these sensors. One of the ways we discussed in the last 2 days was sensors capable of learning. So computational capacity, even in the sensors themselves, so we can have in-skin learning we talked about yesterday, and forgetting, and how important the use of AI is within the sensor itself. And then how do we find meaningful signals when there is no ground truth to measure against? And one of the challenges there are the subjective scales that we administer to people. And so some behaviors can be tracked visually with movement. And we had a number of examples both yesterday and today, how we can understand changes in movement and compare signals across those different states. And we can identify sort of motor delays in children early. And then other signals that can be identified through perturbation. For example, John Rogers talked about the pain of the blood draw in the kids, or we can provoke anxiety and measure cortisol. Right, but others are more challenging because there is no capability for modulation, or the modulation is very slow. And this is something that we talked about yesterday as well as today with the questions that came up. How do we measure internal state? So we have subject variability, noisy data. The data is complex and captured on different timescales. It's challenging to integrate these different signals. And so there's really a need for further approaches, multimodal approaches to help achieve those goals. Along with that is the need for the real world measurements, but how challenging that can be. And this came up in the discussion just before this, and how important context is and modeling context, and the challenges and importance, though, of really getting these real world measurements. And we had a number of really terrific examples: the context aware and personalized AI, the microwave signals, portable radar sensors, and then the longitudinal intracranial EEG recordings that can track signals over days. And then from that, I think there's 2 main questions. This is the third and the fourth main points of how do we get this technology into the clinic? And then the fourth, how do we then understand the brain better from all of these signals and data that we're collecting? And we had tremendous examples of how we're already getting these, using this data in the clinic to measure serotonin concentrations through ingestible wireless devices that are in the GI tract, monitors in the NICU, detecting developmental delay. And then, putting these measures into the clinical trial so we can advance drug development. And we heard a talk yesterday from Biosensics about how we already are able to use these FDA registered medical devices, but that further work is needed to really advance that. Then today, we heard terrific talks on how we can learn about the brain and body function. And so Nico talked about the neural basis of motor control and learning, and really the ability to look at network-based encoding rather than single neuron encoding, and really how tremendous those types of models could be. We heard more about visual perception, both in humans and in animals, by allowing real world, freely moving animal measurements. And we certainly need more work in those areas because, as they've shown today, what we're learning is so different from fixed and controlled settings. And then the last, I think, real point that's has been really discussed multiple times today is ethics, consent, data sharing, the need for the ability to replicate the data, the question of how much data do we need, both at the population and the individual level, and data archiving and standardization, and the efforts, with Neurodata Without Borders and the IE Standards Association to achieve that.
Catherine, I agree with you. There are so many challenges and also opportunities for translation in this space. And I just wondered, Aisha, if you have any additional thoughts or contributions.
Oh, thank you for that great summary, Catherine. Again, I think coming, especially we're looking at the Q&A, I think, the program is called brain behavior quantification and synchronization, but I think with the sensors we have really focused on the brain quantification, and most of the questions that came about were how do we quantify internal states, and the term ground truth came up quite a bit, and then we do know that the clinical scores are done in a very different time scale than the brain function. And we have also, we know that they're also very subjective. So I think one of the challenges we have is how frequently we can sample these, and how whether we could have a bit more objective measures to capture the patient's states. And I think actually the question in the chat is very very on point. So can we actually quantify behavior of physiological functions? So with all the sensors we've heard yesterday and today, we basically can quantify physiological functions, but how each of these functions relate to, again, the internal states, especially in the context of mental health, is going to be really important. And obviously the clinical trials are very important for the clinical safety and translation into humans, but I think maybe this translation could be, faster in the sense that maybe we don't have to, in order to understand how these physiological functions relate to behavior, I think, to expedite the system, maybe while we are working on, making these more scalable, miniaturization and so forth, I think we might also just start with the quantification within the labs again. And then once we have these, that will actually tell us which sensors will be more valuable, and therefore all the efforts and resources could go into those. Again, we know that timescales matter. We know that behaviors basically our interaction with the world, and therefore, the environmental sensors are important. So when it comes to the predictability and forecasting of internal states, I can just give you an example of a Tourette patient where we sent them on 4 different DBS groups. And one week, she just had a really, really tough week at work. And basically, I can just forecast whether her symptoms are going to get worse with, what type of day she's going to have, rather than looking at the brain states. Again, this is the interaction of the brain with the environment, and then the effect of the environment on the brain. And I think the other take home, or the most discussed topic, has been the interpretability of AI. Again, if we're basically going to be able to use this within the clinical domain, first of all, we need to understand what part of the data allowed us to come up with our conclusions, whether we were able to correlate them, or find the causality of them between the labels of the internal state. And basically, actually, one quote that I wrote down that I liked very much, that we can't use AI as a crutch. So as long as we are able to basically translate these physiological functions into the internal states, we may not be able to interpret all the information that we gain from this data and the complex models that we apply to the data.
Aisha, I really appreciate the ideas you're presenting about how best to make sense of the various types of signals and which ones are most informative in order to infer an individual's internal states. I'm wondering if, Jeff, you have any kind of thoughts on the types of multimodal signals that could be used kind of in the mental health space.
Well, I think, good. Okay. It's a really interesting problem, because we have like multiple modalities, multiple sensors, and multiple time scales that they're operating from. And then there's the context, which we haven't talked a little bit about, but I think it needs a lot more. We're trying to understand the person in a context. We're a social species. So that's, other people, and we're responding to them, and we're responding in time. So I think, we talked about standardizing kind of data streams, but, I'd like to see us, think about how to integrate the kind of the sensor streams in a way that, that we can move among them. There was one of the presentations yesterday talked about drift in accelerometers. And, once you lose the synchronization, the data are worth much less. And so so one of the things I wonder is how we can synchronize the multiple modalities, multiple data streams over time. So that was kind of one thought. We also, in terms of sensor systems, 2 that I'm very partial to. One is video, and the other is microphone. And I was really pleased to see in the last session kind of very nice work on especially using video. One of the questions there is how do we collect video in a way that is maximally informative? I think the first person glasses, that were shown, it's an exciting way to do that, to accomplish both kind of eye tracking in a free-ranging animal, as well as recording their conspecifics. Because I think a challenge for us is to understand what people are trying to do and what others are doing and how they're synchronizing that. So I think,
Kirk, do you want to share some observations, that you've kind of had over the past few days?
I think, a few of the talks noted that sensors are not new. They've been around for decades. Clearly, there's been a exponential increase in the sophistication of sensors. And I'd like to believe that we are riding a very upward slope, so to speak, in our ability to use sensors. I think, though, there's a few things that I think are important to keep in mind as we move forward, and one or two possibilities I think that are waiting for us down the road. And I was really, to introduce this, I was really inspired by one of the areas of focus that Dana Green-Schlossler, am I pronouncing that right?
I think so.
Yeah.
That's the way I
there she is. Okay. Noted in her slides describing this workshop, and there's a few points that I think were really important. One, the development and validation of sensors and tools, methods, analytic approaches, precise quantification being a second point, and integration of sensors with simultaneous recording of brain activity in humans and other organisms. In addressing the first point, and a few talks mentioned the importance of reliability and validity. And I think that's a really key issue that we need to keep in mind. I come to this as a behavioral scientist who, with a strong interest in psychometrics, and know that the importance of reliably and validly using our instruments is really important, whether that's psychometric scales or ecological momentary assessments, et cetera. And so I think that's a really important issue to be keeping in mind. And that means kind of cross-validating with ground truth measures as lacking in sophistication as they may be, especially measures of internal states. A second thing that I noted in some of the talks that is really valuable from the point of view of the future is integration of sensors with not just other sensors, but with other modes of obtaining data. And Satra noted this in his talk, the importance of both objective measurement, subjective measurement, with the idea of entraining those two toward intervention. And I think, especially when it does come to internal states, it's really important to be integrating sensor-based data with what's going on in terms of internal states. I think the potential for this work is enormous, as many of you who do this work believe. I'm particularly interested in smartphone sensing, and I think the possibilities for intervention are going to become really explode in their utility as we go forward. Just-in-time interventions, for example, where algorithms that are crunching sensor data can be used to provide feedback to people to intervene when their behavior is putting that person at risk in some way for their physical health, for their mental health. The last point that I wanted to make that's come up repeatedly over the couple of days here is privacy concerns.
And part of my work is in behavioral genetics, and we're coming to a place where just having information on a person's genome can help to identify that person, regardless of whether we have, the classic identifiable data from that individual. And I do wonder whether we may be moving toward a situation where sensor data and potentially combined with other kinds of data could help to identify people in ways that they would not choose to be identified. So that's a privacy concern that I think is important to keep in mind. Stop there.
Well, I was going to mention privacy as one of the most important concerns that has been discussed already in the meeting. And I think it goes beyond just privacy of the individual, as you were mentioning. But if you have sensors that are environmental sensors, then anyone that enters our environment will also have, we also need to discuss the privacy from those individuals. So I think the more we move to this, multi-sensor kind of type of thinking, the more these questions that we use to explore in a very much individual specific realm needs to be expanded, right? Like now these sensors are interacting not just with the person, but maybe with, the caregivers or, the mothers. So I think all those considerations are relevant. I also want to add something that was mentioned yesterday in terms of the informed consent, which I think has similar considerations in that it goes beyond just the individual and it goes beyond, I just need to give informed consent if the sensor touches my skin, right? I think we need to think about if a sensor is monitoring my environment and is collecting information from my body, I think informed consent is also relevant in those scenarios. And the final consideration that I've been thinking throughout these 2 days is the concept of invasiveness. And we usually think in terms of, physical invasiveness, like something that is in the body. But I think when you think about multi-sensors, invasiveness can also be thought of, you have different sensors across your body. That can be perceived as invasive. So trying to get out of the box and think about, will participants like that level of invasiveness to their physiology and body? I think it's important to consider now before we get too advanced and then people don't want to use it. Just a few thoughts in the session. Thank you.
If we sort of take off from there, maybe John and JC could comment on that. I think that there's a couple of things we've heard about. A desirable property of a sensor would be to be undetectable to the user, if possible. And that does speak to invasiveness a little bit if it's physically not detectable. If it's not sending you signals. Some of us wear health devices, for example, to signal whether our blood sugar is low, to signal if our heart rate's gone up. And not everybody appreciates being signaled at all the time. And it does change your behavior. But another kind of meta invasiveness question is just the knowledge that so much data about you is being collected. Where is it going? Who's using it? Who's actually drawing conclusions about you based on that data? That's also something I think that we need to address from an ethical perspective. And I wonder, as people who develop these technologies, what you think about that.
And also, just to add on that, the misinterpretations that could be made about you, right?
Yeah, maybe I could say a couple of words. Obviously, this is the space where, my group is quite active from a research standpoint. So if you think about your patient burden, I think it depends partly or maybe largely in terms of the value of the data and the urgency of the need in the monitoring. And so, we decided to start with a focus on premature babies. A lot of people ask us, why would you start there? That's probably the most challenging patient population in terms of sensor burden, right? These are very tiny, fragile, humans with underdeveloped skin and fragility and so on. But we decided to start there because the need is greatest, for wireless monitoring. And so I think there's a little bit of a balance there. It's not an absolute determination of burden. It's really a function of the quality and the value of the data streams that are being generated. So I think maybe, for envision programs in this space, maybe you prioritize programs in terms of greatest patient need, and that can be a step in the right direction. I think there are all kinds of engineering features that will also dictate, the absolute sort of quantitative aspects of burden in terms of skin invasiveness and, irritation at the skin interface for, non-invasive monitoring, or maybe even these completely contact-free techniques for monitoring. But I think that's an important consideration. And then beyond just the engineering features of the devices, I think patient burden is also dictated by the nature of the user interface. So you mentioned sort of warnings and how much user manipulation is required to actually use and mount the devices. And so systems that can remain on the body for very long periods of time without requiring any kind of user engagement is also an important factor around burden. We deployed devices, a few hundred devices actually, on COVID patients during the lockdowns in Chicago. And one of the things that we found out very quickly is because of the very high levels of fatigue associated with these patients, they had no ability to engage with an app, even a very simple graphical user interface on a phone. It had to be completely autonomous. You put the device on, you don't have to do anything. You take it off, you put it on a charging pad, and it automatically uploads data to a cloud server where all the data can be analyzed and displayed in a very simple fashion. So I think there are user factors as well as base hardware engineering considerations around what dictates patient burden. But again, it's the need that's going to drive adoption and compliance with these kinds of technologies.
On top of that, I would like to add one more factor. So first, let me talk about the privacy issue. My group developed a sound sensor that can be attached on the back to record the lung movements. And then we give it to the doctor in the operation room to use. And after one use, we decided not to do it because it records every conversation of the doctor and nurse in the operation room. So that's obviously not just the privacy of the patient, but also the doctor, nurses, and all the healthcare giver, that their privacy may be in danger too. So this is a bigger conversation. I don't think we can have one single answer here. I think it has to be case by case, because one of the cases we are working on is that the patient basically tell me, I will sign anything you give me for consent because I have this disease. I want to deal with this disease, privacy issue, that's secondary order for them. So how do we prioritize this kind of a need? This really need a bigger conversation, not just among us, but also the clinical society. Second thing I want to raise is, we haven't discussed about this, is not just the privacy, but also encryption, the data. So as Dr. Lee was presenting, that using non-invasive sensing, not just by radar, also we have near field. I don't have to put something on you. I can just be close to you and I can sense your vital sign. I can use optics or acoustic signal. I can detect something without touching you. So now, how do we ensure the data is encrypted so nobody can hijack your data? For example, like we heard people hacking device all the time. What if people hack into your pacemaker or your neurostimulator? So that could be something very dangerous. And we haven't discussed about this part because I think this need to be take place as our colleague in both engineering society and mental health, neuroscience society, make this progress. We need to make sure the lawmaker aware of all this. Oh, did I stop at the dead silence part? I'm sorry.
Panelists can comment on any of these thoughts, or we can also open it up to more general discussion if people have questions or.
Yeah, I had one more point, if I may. We also know, especially for mental disorders, the timescales matter not only for the behavior, but also for the therapy, whether it's pharmaceuticals or, electrical neuromodulation. We know that the patient has to be consistent with taking their pills, and and then if they don't work, they might come back, and the doctor might have to prescribe another one. And same with neurostimulation techniques. They need to be on a defined therapy for a long time, longer than it would take for, say, a movement disorder. So again, I think this quantification is also quite important, basically to guide the therapy and whether we are going in the right direction for the therapy. So I think the aspect of the therapy is maybe a topic that hasn't been consistently discussed.
So, sort of going back to the point about privacy and access to the data, that seems so critical. One of the things, we struggle with is there a way to de-identify and anonymize data in a way that would protect that? So certainly, with respect to video, and instead of recording the full data stream, one could process the video to extract features. Now, some features can be recombined, to go backwards. But many features can't. Now, that would protect anonymity, but at the cost of lost fidelity, right? Because you can't go back when you have a better feature extractor and reprocess. And just like one other approach, the federated learning model, in which all data goes to a protected cloud source, and can only be accessed with, say, approved kind of algorithms. One, I don't know, would that, could such a model provide security?
Actually, this is an interesting question because since I started working on the neural recorder, I got asked this question a lot for the past 15 years.
Yeah.
There's no protected cloud. Any cloud can be hacked. There's no protected data storage. And even though you think you go to VPN, your identity can still be found. So therefore that our engineering society need to think something clever that can protect our privacy and data safety. And I'm bringing this in many conferences when I talk, asking people to think about how do we do this for implant and wearable beyond they want to just protect the bank information, something like that. This part really need to be done, and it has not started yet.
Yeah, I kind of agree with that. I would just add a couple of things. So I think anything is hackable. There are best practices in encryption. We use HIPAA compliant Amazon cloud services for storing vital signs data and so on. I think the better solution is to address it at the level of the hardware, as opposed to reduced resolution or downsampling of the data or encryption and so on. And I can give you a specific example. So we work with rehabilitation specialists who deal with stroke survivors out of what used to be the Rehabilitation Institute of Chicago, now the Shirley Ryan Ability Lab. And many of those stroke survivors suffer from aphasia. And so their vocalizations and talk time, talk cadence, and so on needs to be monitored so that rehabilitation protocols can be tailored to the individual. And ideally, that needs to be done continuously, 24/7. And we were talking to the rehabilitation specialist, and they said, well, could you develop a wearable microphone with Bluetooth? Or said, yeah, we could definitely do that, or you could use the phone. There are 0 stroke surviving patients who are willing to have everything recorded all day long, every conversation. And so the solution was not to do the audio recordings, downsample them, and then just extract sort of periods of vocalization and do things in that way. Instead, we developed a skin interfaced high bandwidth accelerometer that mounts on the suprasternal notch. And so that device is not measuring sound waves, it's actually measuring vibratory signatures of speech at the surface of the skin. So it's non-interpretable recordings, but it has all the kind of fidelity that you would need to determine tonality and frequency and cadence of speech. And that turned out to work really well. Everybody was much more comfortable with that kind of solution. And that same device were actually deployed on opera singers now to monitor vocal dose, to avoid vocal fatigue. Same situation. Nobody wants their conversations recorded all day. And so that was a kind of an example of something that we approached from a hardware side that seemed to be a good solution to this privacy issue.
Yeah, I mean, that's a really good solution. We, we did work on mother-infant interaction, in which in both the mothers and the infants, we did glottal. We used just sensor over the glottis, which I think is what you're describing, and it produces what sounds like whale talk. So it's going right. So there's no kind of linguistic information there. But it's very good in terms of kind of speech rate, timing, and we found it had very high correlation with microphone data as well.
Just to note that it's sometimes difficult to see you all, so I just noticed. So why don't we take a question from the floor, and if a long time goes by, maybe wave or something. It's just very difficult to see, but. Go ahead.
I'm James Massing from City College of New York, and I study brain-body interaction. And I use a lot of different sensors modalities. I've tried out new sensors, and one of my biggest problems is to make these sensors talk to each other and time align them to one another. And one of the challenges of taking neuroscience out of the lab and still study this brain-body interaction is to have a way to have these sensors talk to each other. And we've heard all these wonderful sensors being developed, and I would love to wear all of them all at the same time. But how do they talk to each other? Can we just readily go out and take one of your devices and then synchronize them with all the other devices that are out there? Another thing would be sort of time precision. Another thing would be, can we have multiple devices synchronized in time with each other? So we could do simultaneous recordings, like record all the heart rates of the audience right now to see how it reacts to all of those wonderful speakers. I'm just curious if you want to comment on that.
Anyone can take that. Also, speakers with expertise on these questions, like with expertise on Internet of Things, systems design, please come to the microphone and join the conversation. But who wants to take that one up here?
Yeah, I can say a couple of words. Somebody else may want to weigh in as well. So I think you asked kind of two questions. One relates to interoperability of devices, maybe from different vendors or from different labs. That's kind of one set of issues. And then the other one was just time synchronization across multiple devices on an individual. So for that latter challenge, I think it's more or less solved. It depends on what level of time synchronization you're interested in. So we have body area networks of devices. So for monitoring neuromotor behavior in these infants who are at risk for neuromotor delays, we have 11 devices mounted to different body positions. So we can reconstruct from the accelerometry and gyroscope information from all 11 of those devices, full body motions in avatar form. But then we have the raw data, we can do machine learning. In that case, we have one device, and I think the terminology might not be quite right these days, but it's master device and slave devices around it. And so there's a clock exchange that happens from the master device to all of the slave devices, and that happens 10 times a second. And so there's no drift, there's no long-term drift. There is some latency associated with the way the Bluetooth system on a chip components handle packet exchange and information. So you can get time synchronization down to about a millisecond, which is good enough for like kinematics and body motions. It's also good enough for pulse wave dynamics. So pulsatile blood flow, hemodynamics is pretty good for that, as long as you have a large enough separation between devices so you can measure those delays. I think doing better than about a millisecond probably requires a hardware modification. It's not something you could probably address with firmware or software. But if a millisecond is good enough, that's a solved problem. You can do that. And we do that routinely. I think probably other groups as well for hemodynamics and full body kinematic measurements. So the drift issues kind of go away, timing drift at least. In terms of interoperability, I think it maybe comes back to some of the standards conversations that we were having earlier, a little bit more focused on data, but probably standards in terms of how devices from different vendors can communicate with one another. I think that's a much bigger challenge because it requires coordination across multiple companies within the industry. What we see is there's a tremendous amount of interoperability, even in ICU monitoring devices that exist in the most sophisticated NICU, PICU facilities or ICUs in the US. You have the pulse oximeter, and you have the GE dash that's doing the ECG, and those do not talk to one another. It's very difficult to get even raw data streams out of them. And so interoperability is much more challenging. I mean, we have like a whole suite of devices and they all talk to one another because they're being produced out of my group. I don't know that that's necessarily a solution that you're looking for, but we appreciate it as a problem. And I think having devices that all operate on a common hardware platform is very important. I think maybe one final thought along those lines. I think there's a real need for interoperable platforms that can be used by the research community. There's all kinds of incentives for companies to have their own proprietary protocols and so on. But if you could imagine like a modular system where you have sort of like a base station that has your power management integrated circuitry, the battery, the Bluetooth SoC, let's say, for example, and then you can just swap in different sensors into that base unit. The base unit determines operability, and then everybody can throw their sensors into that same kind of base unit. I think that would be a very powerful resource for the community.
You can imagine like an Arduino, wearable Arduino, but you can actually, all sensor developers could talk to that device.
Something like that, yeah.
Yes, I agree with John. We are using the same approach, using Bluetooth for data synchronization. It can go down to 1 millisecond accuracy. And we do find out that one thing interesting is that the data storage writing into the hard drive that actually delay more than 1 millisecond. So then that kind of destroyed that part. So that's why we need to get bigger and bigger hard drive every time we do the longer measurements. Also, there are several vendors now they realize this problem, not just Arduino, that's a very low-hanging fruit. Also, like Texas Instrument now is developing this module. They can plug in 6 to 9 different sensors in one single module, and they do the synchronization internally. So that way, you can get different sensors from different vendors, and the hardware take care of your synchronization issue. So I think that as this field keep growing, I think more and more vendors will come up, provide that kind of platform solution.
Before we take your question, I did want to return to Aisha's comment about different time scales, because I don't know that it was something that we fully addressed. And that is, there is the therapeutic time scale, not the same thing as sort of the minute by minute behavioral time scale. And one big question is, how do they relate? If we only look at the therapeutic time scale, and then just check in on a week or monthly basis, we already do that. We don't need all this fancy stuff to conduct therapy when checking in on such a slow time scale. So the question becomes, how do all these fast events that might be embedded into these very slow changing events that are therapy or response to therapy, how do we actually model whether therapy is being successful based on the relationship between those fast events and this very slow course of improvement?
Right.
Maybe
Want to start?
Yeah, and it's very important for us to basically reduce the time to therapy.
And another challenge that also goes along with that is that the changes in neural signals or mood or internal states might not be temporally locked to an event that leads to them. So understanding, how you might have change in heart rate immediately after a negative event, but it may be a delay in a day before that manifests in a change in mood. So understanding all those time scales is also really challenging, even independent of a drug or stimulation.
Exactly. So that basically there are multiple different kinds of correlations that can occur across those timescales. Something fast that happens today might be actually causally or predictably related to something slower or faster that happens tomorrow. So that the multiple correlational structures that are available across these timescales are daunting. And we just, how do you all think about that? And I know that Kurt had a reaction. Sorry.
Yeah, just speaking from a mental health perspective, it's true. The clinical course of the condition can be quite slow. But often I think what we're relying upon when we look at that time scale is a person's own self-referral, for example, to a clinic, or another kind of indicator that may be too slow to really effectively intervene in that mental health condition, potentially even when it comes to sensors, potentially even before the person knows that they're at risk for a condition. So I think that's where sensors can be potentially very valuable to indicate that a person may be at risk for a particular depressive episode or what have you. So for example, we're doing work and others have done work showing that just having information on smartphone sensors like GPS and call and text logs, et cetera, are quite good predictors, not perfect, but 80% accuracy in predicting who's going to have a depressive episode. So if you can potentially change the time scale, alter the time scale so that the clinical time scale becomes more in line with that moment-to-moment quantification of information, of behavior, and potentially, not just treat conditions better, but potentially prevent them or ameliorate them. Yeah.
And perturbation, I think, is also really important and a useful tool, especially on a personalized level, trying to understand, behaviorally or just through conversation, what triggers a patient to feel or induce certain motor states or behavioral states or internal states. And then repeating that so you can have more trials and try to constrain the context in addition to using brain stimulation, stress tests, other types of perturbations, pharmacological perturbations that can help constrain the context and sort of reveal repeated events that you can then help match the timescales of events and integrate the signals.
This notion of like therapeutic time scale, is an interesting one because it comes out of a model of assessment of doing a Hamilton interview at so many weeks intervals. Yes. And when we talk in terms of depressive episodes, we're implying that there's a continuous state until that transition. And yet there's a lot of variability. We don't know very much about it. And it seems one of the really exciting things about the move towards sensors is to understand something about what are the temporal dynamics of a depressive episode. And are people, coming out and then just going back down? And is that a motivated thing? So I think we shouldn't force the sensors to kind of conform to preconceived notions.
And I see Sylvia
who I'm sure has also some thoughts on this as well as the question you had in mind.
Yeah, no, I think that is such a great point, capturing different timescales of events and capturing things like internal states and intra-individual variability is quite challenging. I had a question that maybe moves us away from this topic a little bit. So earlier in the morning, we discussed issues of standardization that has to do with harmonizing the format of our data to facilitate data sharing, for example. But I was wondering what thoughts you might have in terms of harmonization of analysis pipelines as well, because I think that there is a lot of degrees of freedom in terms of how we even just pre-process and analyze these signals. And a lot of us are using essentially the same signals, right? We're interested in heart rate variability and skin conductance and accelerometry and maybe voice analysis. And, to some degree, there's no point in reinventing the wheel. So what kinds of thoughts do you have, and whether as a field we should try to move into harmonizing those practices?
I mean, I can take a stab at that. I mean, my group is more focused on issues in material science and circuit design and hardware and that kind of thing. And we do data analytics when we're forced to do that, which is frequently, but that's probably not our main strength. But, we develop neural networks, various kinds of machine learning, state machines, digital filtering, pretty standard approaches, but kind of tailored to the use case. So, for example, with opera singers, we need to measure vocalization, but separate them according to whether it was a singing event or a speaking event. That requires a machine learning model that you have to apply to the time series data. So it's a little bit tailored to the use case, and I think maybe that's an example where it's pretty specialized. Maybe there are other people who would want access to that. We post everything to GitHub, so we're an academic group. Everything is out in the open. It's not, in some cases, maybe packaged with a user-friendly interface. So that may be an area of need, that could, cut across broader efforts beyond our own, where the algorithms are there, but the user interface just doesn't allow, access by the broader community. But we try to open source everything we do. I think most academic groups have that orientation at OJC.
So can I just, so I appreciate that. Right. And the majority of groups have their own packages and pipelines. A few years ago in the neuroimaging field, we encountered, this crisis in the field coming from the fact that everybody has their own preferred pipeline. And that results actually in issues of reproducibility. And so yes, we tailor things to our own personal questions, and each research question is different. But to some degree, if we are using the same physiological signals, it could be interesting to posit whether there should be some harmonization in what we do with them.
Yeah, definitely. I agree. I'm not arguing against that notion, but just try to think about the best mechanism for achieving that outcome. For vital signs and more traditional measurements, maybe heart rate variability, things like that, there are gold standards to compare against, and so you can develop different algorithms, but ultimately they have to produce the right answer. So that's an important constraint, I guess, as well.
We're gonna transition to final thoughts. Do you have? You've been standing here forever, I feel like.
So let me. Could I answer just one sentence? IEEE has a lot of working group try to standardize the process. So today, Bruce only mentioned just one very small part. Actually, there's many group working on ECG, EEG, all different signal processing.
Go ahead. That was my initial reaction to Sylvia's question. That sounds like a good job for a work group. Sasha, do you have a question?
Maybe this will lead to final thoughts. So I'll frame it this way. Can we reframe the conversation around privacy, around thinking about sensitivity and risk
and benefit, and kind of think about it through the lens of what design principles should govern our generation of data, sensors, and computation around it, because all of this is going to get integrated. We are currently seeing these as separate streams, but they are going to come together. So could we kind of think about reframing the conversation a little bit around sensitivity, risk, and benefit, and how the sensor community and the data analysis community can come together under some of those principles? And would that be a set of actions that this community could take in the short term to say what the principles should be under which such devices and computation should be designed and developed?
I would add that you will need to bring, the potential users to that conversation as well, right? Because developers might have assumptions of what might be good design principles, but maybe they not necessarily overlap with those that the users might, agree and be comfortable with. So bringing those early on, I think, would lead to a better set of principles for designing. So, but yeah, that's a great way to reframe that question.
I know you're out of time, but I was wondering if I could say just something briefly. I think I'm one of the few MDs in the audience, and I think it would be important to partner with physicians as well. So I'm hearing this not only as somebody who might wear these, but who might treat somebody who wears these. And there are all kinds of issues that have not even yet been addressed here. For instance, if I treat somebody and they have this huge data, what is my responsibility as a physician to know those data, to interpret those data? Standards have to be set for that as well. And if something's not accurate, I'm not telling my patients about it. And privacy is an issue. And Satra, you said you'd wear all the sensors. I would wear none of them. So I just wanted to put that in there as well.
Good place to I think, wrap up.
Yeah, so next we're going to have your final remarks, closing remarks. JC and John, you can go ahead and stay here or go to the podium, whatever you're comfortable with. Sure. Thank you to all the panelists.
First of all, thank you all very much to stay in this workshop for 2 days. I couldn't express more appreciation to all of you. Many of you I know for years. Many of you I just make new friends, and I hope this workshop bring everybody together. So let me do a very quick summarize what we have talked about. We talked about hardware development. We heard about wearable, implantable device, component, systems, software, and we talk about signal processing and multi-sensor platform. And we also had several demonstration of clinical application. And then we also heard the need for energy consumption, power harvesting, and also interconnection between network and data transmission. And then because data are massive and in big quantity, they are very noisy. So we heard about using machine learning and AI for processing, and also using computation model to analyze, predict, understand the behavior. And it was very nice to see all this animal model being studied. So if one of you finds a non-invasive way to detect why my kitty cat doesn't like to use litter box, please, I would love to volunteer experiments. And then we heard about standardization, all different effort by different institute and university, try to synchronize everybody's data stream. And then we talk about the future development. And of course, in this workshop, when we first started, it was a coffee table conversation. We tried to bring people together. And so we can only invite a limited group of people. So there will be quite a lot of people we have not heard from. And also for the people we invited, could you put up the slides for the profile paper? And also for the people we invited to speak and discuss, we really don't have enough time for you to disclose your research in a comprehensive way. So therefore, as in the beginning, I mentioned that I encourage all the presenter, discussants, coordinator to submit a paper. This paper can be about overview or review what you have talked about, your sensor development that is suitable for study complex behavior. This paper can be submitted to IEEE sensor letter. This journal is target for quick turnaround, more informative to everybody who's in this field to have a very quick understanding what each other is doing. The paper deadline is July 1st, and we're trying to get this out to disclose to the world what we are doing by October 1st. And so if you have any question, you can contact one of us as a guest editor. You are also welcome to go to the website. If you have not submit paper to IEEE use Scholar One portal, which is quite intuitive. At the portal, it also will have a list of the topic, and you can choose your topic. And we can have a quick conversation to see that if your paper is suitable or not. But I do encourage everybody doing this because this will have a formal documentation that for this workshop, and we can also let more people to know what we are doing and what we are looking for. So in this workshop, because of limited of time, we did not actually include some of the topic I was interested. For example, assessment of subjective feeling. My research is working on closed loop inhibition of chronic pain. So we record the pain signal and we trigger the neurostimulator to inhibit pain. When I was doing that, I was also thinking in the sensor society, actually we are doing that already. For example, you wear a smartwatch and you look at it, oh, today I only walk 4,000 steps. Maybe I shouldn't take the bus or Uber, I should walk home. Now the sensor is correcting or modify your behavior. So this kind of a feedback mechanism we have not talked about, and that's simply not by anything did by the hardware, but by your conscious that you modify your own behavior. So this is the topic we didn't talk about, and I was hoping that if we have researchers that's working in this field and they can tell us what they have been doing, and maybe this will start another conversation. We also didn't talk about the subjective feelings such as anger, depression, frustration. Those feelings can be amplified if they don't have sensor to monitor them. Sometimes we are so angry, we don't even know we are angry, and we might have outbursts doing something we regret. And therefore, that I think what we're doing here with sensor can actually help somebody to meditate their own mental state. So this is something I was hoping that if there's a researcher out there working on this in this field, can shine some insight to the sensor society and also for the neuroscientists studying this field. So before I close this, I was sitting here, I couldn't feel anything but very proud of ourselves. We are all working in different fields, but we come together to solve several very serious problems, not just disease, but make our society better. So we are not working for ourselves, we are working for our children, our grandchildren, our friends, our family, our society. And we're not just working for America. We are working for everybody in this world. So I think we should give us a pat on the back, and knowing that today when we go home, we are doing something really great for this world. And now I will let John summarize his thought.
Yeah, thanks, JC. I know we're running behind time, so I'm going to go pretty quickly here. But I really like your vision of some kind of device that will allow you to modulate your stress level, because I can imagine if I'm wearing a few sensors right now, my blood pressure and stress level is pretty high. It'd be nice to be able to drop that down somehow. But let me share a couple of thoughts, one kind of programmatic and one kind of focused on technology and engineering. And so the focus, of the last 2 days has been sensor technologies, right, to capture complexity, behavior. And kind of what I saw was not necessarily a complete bifurcation, but two classes of efforts. One kind of at the level of, academic frontier level research on sensors. And then on the other end of the spectrum, you have sensor development happening in commercial settings, and in many cases very sophisticated, but much different styles of research. The commercial systems tend to be locked. They're not interoperable. We're just talking about that. A lot of times you don't have access to the raw data streams. The academics are much more open in that sense, but they're also much less capable in sort of scaling and providing availability to the broader community to their new and novel device technologies. And it really was kind of apparent to me in this last session where we heard about these really, advanced, exciting studies on behavior and brain activity, where most of the work was, using Utah arrays, well-developed technologies, in many cases commercially available, or on the other hand, sort of neuroscience, behavioral-oriented research groups trying to hack together, engineering solutions. In many cases, look very sophisticated, but it would be much more powerful if you could develop, funding mechanisms. And I think maybe this is a role that NIH could play that would bring these two communities together in a more intimate fashion, so that sensor developers and engineers could be working directly with behavioral scientists and neuroscientists on hypothesis-driven questions, around sleep or pain, and stress, neuromotor disorders, dementia, neurodevelopmental progress, and brain-gut axis, for example. Maybe rank ordered according to greatest medical need, because I think that would help drive the academic community to sensor modalities that are really moving the needle and having a realistic impact on these kind of behavioral studies. And it would also force them into a mode of not just developing, and this is not characterizing the entire collection of efforts, obviously, but in many cases, developing sort of hero level one-off sensors that kind of terminate with a publication, but more in a mindset of trying to develop systems that can be produced at quantities that really allow a broader utility and more greater impact, in terms of understanding the relationships between the complexity of behavior and brain function. And I think over the years, you would ask, okay, what does a success story look like? And I think if you think about sort of the combination of Florian Sulzbacher and Krishna Shenoy, that was a great example of neuroscience coming together with engineering, or Brian Lidd and John Vivinti, another example, neurosurgery and bioengineering, for example. And in many cases, those technologies eventually, gain traction and have some kind of stable commercial foundation for their continued propagation. But there's kind of a gap between that initial discovery and, scale that really allows for that commercial translation. But you've seen it happen, over the years. BlackRock is a great example. NeuroPixels, Florian and Tim Harris in those cases. We've been involved in that kind of thing through Neurolux and optogenetic technologies. Inscopics was a technology that emerged out of Mark Schnitzer's lab. So it happens, but how could we set up collaborative funding vehicles to make it happen more frequently? I think that would really have a big impact on the broader community, bringing engineers more closely and intimately connected to behavioral scientists and neuroscience scientists and so on. So that was kind of one sort of programmatic opportunity that I came away with, and I'm sure others have different opinions and thoughts around our discussions over the last couple of days. But it's just one thing I wanted to share with the broader community. The other one has to do with engineering topics more explicitly, and less about programmatic opportunities. And that would be like, where are the grand challenges? I think we heard from Nico and we heard from Avniel and so on. You know, what is a solution? What is a non-invasive method for collecting electrocorticography? Like how would you go about doing that? And could you develop skin interface devices that offer 1 million channels of EEG data? And could you use those million channels to sort of triangulate and capture high frequency, spatially localized information on brain activity? That might be interesting. Or maybe incorporate arrays of pixels and combine electrophysiology with optical measurements of brain activity. That might be a grand challenge. How do you do non-invasive ECOG or non-invasive Utah array type measurements? That'd be a pretty exciting development if you could identify an engineering solution to that. And then the other one has to do with biochemical markers of brain activity. Could you develop something that looks like a CGM but is monitoring dopamine or serotonin or something like that in a continuous way? I think that could be exciting as well. Sweat may be sort of a non-invasive biofluid that would serve as an alternative to interstitial fluid, but I think CGM technology is gaining a lot of traction. And could you sort of leverage that for measuring brain activity? But just to conclude, I think I want to extend again my thanks to the co-chair here, JC. I think he did a lot of the heavy lifting with Yvonne and Dana to put this together. And thank all the speakers and the panelists and the discussants and the moderators and so on. It's been a tremendous event, and I've certainly enjoyed it quite a bit and learned a lot as well. So thanks to everyone.
Before I would like to thank our NIH colleague. You sacrificed a lot to put this together. I cannot express how much I appreciate this effort. Thank you.
Okay, now for our concluding remarks, I just want to introduce Dr. John Nye. He is the director of the Brain Initiative, and he oversees the long-term strategy and day-to-day operations of the Brain Initiative and strives to revolutionize our understanding of the brain in both health and disease. I'm not going to go through all his accolades, but there are many and a lot if you want to look on the bio sketches and abstracts. And with that, I give the floor to John.
Thanks, Dana. I want to thank our co-chairs and our entire planning committee for putting on a great 2 days of science and engineering. It's really been wonderful. Also been wonderful to be in person with at least some of you. Whether you arrived here in person or via Zoom, we have to thank our partners at Bazell for making it all happen. So thanks very much to you folks and for the staff here at Natural for making everything here work quite well. So this is our first hybrid meeting since the before times, and I think it worked out quite well, and I look forward to more of these coming up in the future. So if I may have a slide. Great, thanks. And I can drive here by clicking, I imagine. So I just wanted to give maybe, given all the summarization we've had over the last 2 days and all the detail, what normally I'd consider a 50,000 foot overview is actually a 100,000 foot overview, so bear with me. So I think what we saw here was the introduction, a reminder of a lot of new technologies that have been developed by engineers, as well as novel use cases for technology applications by the neuroscientists. So I think this is really a great substrate for follow-up discussion. So in a way, I feel this meeting was really successful in that these ideas got put out. There's a lot of discussion, but the real measure of success is if you folks can start talking to each other and put together projects that are going to result in real impacts out there, both in the research domain as well as in the clinical domains. We heard a lot about the needs. We heard a lot of really cool technologies. I think let's marry the cool tools, the possibilities with the applications. I think we can actually generate the mother of invention here for additional technology development. So I really do encourage you folks to continue talking, and NIH Brain will do what we can to help facilitate those discussions and those projects as they come along. So the next point, one thing that I think will assist a lot in bringing folks together from these diverse backgrounds and disciplines will be the formation of multidisciplinary teams and consortia. And I think this will not only lead to better ideas, but also the more rapid dissemination of these ideas. And to the extent that you folks can work in the so-called pre-competitive space, as the saying goes, better to have a piece of a big pie than no pie at all. So I really do encourage you folks to think along these lines. We heard some great discussions, and it could take up an entire meeting of themselves, about data use, reuse, and sharing, and all the things that go along with it. And I think the really important thing to bear in mind is not to think about this after you've done your experiment, right? After you've made your device. I think a lot of these problems won't get solved unless we think about these issues of data reuse and ethical use of these data at the outset. So I really encourage you folks to be thinking along those lines. And the next, I think I'm driving here. There's a lot of discussion about data standards. As an old colleague of mine once told me, and I'll paraphrase, I think people would rather share each other's toothbrushes than each other's data standards. But we need to overcome that. Yeah, it's kind of gross, right? So we need to overcome that. And I think this is really an opportunity for social engineering. We need to start thinking differently about how we do science as a community to solve these big issues. I mean, I think everybody came here with articulating great aspirations for what they can do with their technology, with their science, but it's not going to happen. We can't solve this. And it really will take a village mindset to solve this as I think one of our biggest challenges. And then finally, we do really need to incorporate our thinking about what the impacts of our science is. Ethical, legal, societal impacts is very important for what we do. And again, another example of what we need to be considering at the outset before we start an experiment, at the initial level of conception, in order to make sure that we do things in a way that's going to be beneficial for not just our science, but for the folks that we purport to help. So I encourage you to think about that. Brain takes this very seriously. We have an active neuroethics working group that gives us great input about how to think about these issues, both prospectively and sometimes admittedly reactively. And you can learn a lot more about that as you follow what Brain does. Okay. So just a few plugs of our own. Next slide, I may. So just a reminder, we have our annual Brain Initiative meeting coming up in June. Anybody is welcome to attend either virtually or in person. It will be in North Bethesda, June 12th and 13th. It's going to be packed with 3 plenary lectures, 6 symposia, and 3 concurrent sessions, trainee highlight award talks, and a lot of opportunities to network and talk science with each other. And this is the first time we're back in person since 2019. I think people are really excited to be coming together and having discussions of the sorts you've had today. I just want to mention we have 3 terrific plenary speakers lined up that actually address many of the issues that we discussed here over the last 2 days. So on the left is Dr. Vanessa Ruta from Rockefeller University, and she's going to tell us about her really exciting work on the modulation of neural circuits and behavior using the fruit fly as a model system. In the middle is Professor Anita Arhani from Duke University Law School. She's a very prominent ethicist, and she actually specializes in this area of data privacy and data use in the neuroscience space. She just recently published a book, and she talks not only about data privacy, but this concept of cognitive liberty. So I encourage you folks to at least tune in for that talk if you're not there in person, for some really, I think, insightful and provocative thinking about some of the issues we discussed here today in terms of how do we deal with data from humans. And then finally, Dr. Samir Sheff from Baylor University, who's at the forefront of using various invasive technologies for treating neuropsychiatric disorders and other conditions. So I think a really exciting set of speakers for the plenary talks, but really great opportunities for folks to get together and network. So I encourage you to attend either virtually or in person. Okay, so next slide, if I may. So there's plenty of ways for you folks to learn about what the Brain Initiative is doing and the kinds of science we're supporting. If you don't mind a little bit of extra email in your inbox, you can subscribe to these various features and you can learn more about us on our website. The next slide, at Brain Initiative. www.nih.gov. So again, thank you all so much for being here. We really had a great 2 days of folks, both in person as well as virtually, and we look forward to gathering with you again in the near future. Thanks very much.
So in closing, let's give all of the speakers and discussants a round of applause for outstanding discussions. And next slide, please. Again, going back to some of the logistics of this whole meeting. Again, John, thank you for sponsoring this workshop with the BRAIN Initiative and the NIMH for sponsoring this workshop as well. And here, some of the folks behind the scenes in science policy, putting together the travel for you, our contractor, Bazell, NIH Events Management, and BRAIN OD Communications, and our caterer. So thank you to them. And the last slide too, just another what Holly mentioned this morning, all of the program officers who worked together to put together this, this meeting, and I couldn't have done it without them. And hope you got to meet them all. So that's it. And we will be sticking around until 5, or if you want to have some more discussions, and there will be more discussions to follow. So thanks again, everyone.